Right. So in the first part, like what I mentioned before, like it's not too interesting. Like the only thing is that like I'm a PyTorch core maintainer. So if you're interested in like open software, I work for a company that does open software. So if you're interested in that, like just if you are not here, shoot me an email. If you are here, contact me. And I also do optimization on manifolds, constraint optimization. So if you are interested in constraint optimization, also like I really like all this stuff as well. So yeah. Anyway, like going back to this, like, well, this is the usual model for least squares, and you can compute the gradients of this simple model, and you get those gradients. And you're like, all right, and you can compute it by hand, but like there is certainly some structure to those gradients. Like for example, there's a matrix vector multiplication that in theta. And there's a priori, there is no reason why there should be that matrix vector multiplication. Like the X is just the matrix of all the vectors. So a priori, there is no reason for that matrix vector multiplication to be there, because if you remember, and I will go over that now, again, like to compute gradients and stuff, like you need to compute Jacobians, and you do Jacobian vector product, but that is not a Jacobian vector product. Like that is a matrix vector multiplication that appears after you do a Jacobian vector product and you get a vector, and you are like, oh, actually this vector I can write it down like this. So there is some structure there, but it's no clear from the Jacobian vector product and all that stuff, like why it's that. So that's one of the things that we're going to touch on. Also, like you have a neural network very badly drawn, and you have like as data, you have like pictures of cats and dogs, and then you have like a model that's just a few linear layers with non-linearities. And now you have like plenty of parameters. You have like quite a few matrices, and you have like a few vectors, and the loss function, let's say that's the cross entropy for this model. Then you are told, all right, compute the derivative with respect to the kth matrix. If you do it like coordinate, you can do it, but like it can be there, for a week and a half, and then like you actually like after a week and a half, you'll end up discovering like what we'll actually discuss in this talk. You'll see the patterns, and you'll say like, oh, like this happens done. But like if you are just computing things, like coordinate by coordinate with coordinate, imagine like differentiating this with respect to the first A, like the innermost A1, like it would take so much time, and like there just must be a better way of doing this. Like, also the intuition behind all this coordinate-free approach is that, like you don't talk about coordinates, you don't talk about the coordinates of a matrix. Why would you, like from a computational perspective, why would you want to not talk about the coordinates? Like GPUs and CPUs are good at doing things in parallel. And like in particular GPUs, they are good at doing the same operation in parallel, but like not different operations. CPUs are good at doing different operations, and with some parallelism, GPUs, which are what we use in deep learning, and TPUs even more. Like they are very good at doing like one operation, but the same operation, all across. So if you just say like, oh, I need to compute the gradient with respect to this element, and like I'll compute first that part of the gradient, and then with respect to the second element, of a matrix, and then you have a massive matrix. You would need to call like so many operations, and certainly not in parallel, and that would be terrible. And then deep learning wouldn't work. So like there is some structure that allows us to just compute the gradient with respect to a whole matrix, just doing like matrix vector products or matrix multiplications and stuff like that. So there must be some structure there, because otherwise, again, deep learning wouldn't make sense at all. So that's what we are going to discuss in talk. So the talk is going to have like an introduction, as I said, which is like a review of multivariable calculus, and we're going to discuss the gradient, the Jacobian, the chain rule, and also linear maps, just to gauge here, like how many of you are like, well, gradients, I reckon that like you all know, but like who knows the definition of the Jacobian? All right, so about I mean, like, yeah, so we're going to, again, like, we're going to go through those, and perhaps, like, if you have a more mathematical background, like, the first part of the talk might be a little bit simple. Hopefully, the second part of the talk will be more interesting, even if you come from a more mathy background. Actually, the second part of the talk and all this coordinate-free approach is what serves as basis of the theory of differential geometry and Riemannian geometry, really. So if any of you are interested in those things, or like have taken a first course about those things, these things may, you know, you might be more comfortable with these things, but hopefully, like, even if you don't know what those things are, and you certainly don't need to know what those things are, like, these things hopefully will be understandable and interesting. And the idea is that the second part will talk about forward modality and backward modality from this coordinate-free perspective. And the coordinate-free, as I mentioned, just talks about, it's the idea of talking about matrices rather than as matrices. I'm thinking them as, you know, like having entries and columns and rows and all that stuff. We're going to think about them as linear maps. So linear maps, we're going to define what a linear map is. Just for those of you that are not comfortable with that concept, but like it will be basically a different perspective on the concept of a matrix, on the concept of a matrix vector product, and so on. And then, like, we'll use those concepts and like a few tweaks on the definition. So we'll basically restate the definitions of the gradient and the Jacobian in a more abstract way. And using these more abstract definitions, we'll basically like start milking them to get all these results without, you know, and we'll barely compute any derivative, really. Like, you'll see that everything will follow from the definitions. Again, like, you have to think of this as C versus Python, you know, like first pass with coordinates and so on. C, you know, like you have to like handle all the coordinates of a matrix, and so this or, you know, like, or against Haskell, let's say, because like it's a bit more abstract, but like it's difficult to understand at the beginning, but then like gives you like so much more. So so all this, the second part is going to be like basically we'll revisit exactly the same context, and like if at some point you feel a little bit lost and you are like, oh, what's all this stuff? Like, just think of the things that you already know, because we are going to be talking about those things with different names, and those different names will basically be stressing all the properties, which are basically will be stressing the important properties of this Jacobian and all this stuff. Like, we'll disregard the properties that are not important, and we'll use a notation that emphasizes the things that are important. And like you'll see that, like, the second part, basically, it will be like putting a type system onto our functions, you know, like not every matrix will be equal. Like there will be some matrices with our linear maps and others that will be treated as vectors, you know, like flattening a matrix and so on. We'll see more about that. So, all right, first a few things. Vectors in Rn will be denoted as columns. That will be important, but it's a standard thing that you do in maths. We will use a little bit of notation from differential geometry, which is a very small, like a very small piece, that we will say that function is a map onto the real numbers, not into, so we'll just have one output, and we will differentiate those from things that we would call maps or differential maps, differentiable maps, but like just simply a map that will have like k outputs. So the idea here is that there's some concepts that will be just defined for functions, and there's other concepts that will be defined for general maps. And of course, a function is a map, but a map may not be a function. So we'll use, just for notation, just so that it's easier for you to follow what's what. We'll try to use the letter F whenever possible to denote functions, and the letter E and H to denote maps, just, you know, to be able to track better what's what. So the first definition, the gradient. you already know this, not too exciting, but the gradient, like the important part here perhaps, that the gradient, we just define the gradient for a function. We don't define, like gradients just defined for a function. And we'll see later on, like what is the generalization of the gradient for a map. But the gradient is just defined for a function onto the real numbers, and the gradient is a vector. The idea of like why is the gradient just defined for a function? Well, the gradient has a very geometric intuition. Like the gradient is the direction of graded ascent, but like you cannot talk about ascent or descent and things that are not functions. So, it doesn't make sense to talk, geometrically, it doesn't make sense to talk about gradients of things that are not functions. So, gradient is a vector, and like geometrically, the direction of gradient is ascent. So gradient descent, you take minus the gradient, you descend, etc., etc. So it's just a vector of partial derivatives evaluated at points. A few gradients, right? The gradient of a sum of a few numbers is just a vector of all ones. There's different, like the first coordinate, different derivative with respect to x1. We just have one if the derivative is 1. All right, that's it. Same thing with all the others. Vector of all ones, not too interesting. A slightly more interesting one that will be like our recurrent examples, or one of our recurrent examples during the talk, is the gradient of the scalar product of the x transpose times x. That's the square norm also of the vector x. So f of x in coordinates is just x1 squared plus x2 squared, but like in a more coordinate-free approach, just x transpose times x. The gradient of this is just 2p, because the first derivative is just 2 times, evaluated at the point p, is just 2 times, well, you compute the derivative with respect to x1, which is 2x1, and then you evaluate it at p, so it's 2p1. And same thing with all the others. I'm just like, for now, like at the beginning of the talk, I'm just using 2 different letters to denote one. Like I'm using the x1 xn notation to denote like the free variable in the function, and then like when I'm evaluating that, I'm using the variable p. Like usually here, like in the definition of the gradient, you see that you just evaluate at x and you differentiate with respect to x. That is fine when you understand what that is, but like you're using the variable twice for things that are just very different. So like here, I'm using the variable p to denote the point at which I'm evaluating the gradient, and then the partial derivatives, I denote them with x1, xn. Slightly different derivative, like the hyperbolic tangent, and so like this is just like a slightly trickier derivative. I just put it there to show you that like this is really like all that we are doing here at the end of the day. Like this partial derivatives is just partial derivatives you differentiating with respect to one variable, leaving all the other variables untouched. So all we're doing is differentiating functions from the real numbers to the real numbers, as we're taught in high school. So there's nothing fancy here. Like perhaps the formulas are trickier. Perhaps it takes longer to get those formulas, but like the maths behind it, like they are just very simple. So this is just a slightly different one. The derivative of the hyperbolic tangent is 1 minus the square of the hyperbolic tangent. I had to look that up too if I don't remember these things, but like the tables for these things. So you denote the hyperbolic tangent of the result evaluated at p, of the function evaluated at p. So it's 1 as u. It's 1 minus u squared times the derivative of what's inside the hyperbolic tangent. So just differentiate that. Yeah, it's not too interesting, but it's just to show that like this works with more difficult functions, and like you can go further and further and further. But like my point here is that all the gradients, even if it takes longer, they are computed the same way. So even if we are going to use like higher like more abstract tools in the second part of the talk, like all that we are doing is computing this quantity, no more, no less. And sometimes you will need to go like deeper and like low level and like use these tools to compute, like, go to the definition and like compute the things using the definition, like in some slightly more complicated functions. But the whole idea is like, it's like when you know how to program well, you use like the highest abstraction that you can to solve a problem. But like, also like the lower abstractions in case you need to, like make things that are like tricky that, work with the operating system well. So yeah, gradient. So exactly the same thing, but for matrices. What if we have a function that depends on a matrix rather than a vector? To the x of the derivative, these things are exactly the same. So for example, like if we have a matrix, like this is, like we can flatten the matrix. This is called flattening the matrix. And like you just kind of like a matrix is just a very long vector. You can put it, like the first row, then the second row, or like column or whatever, however you want to order it. You can flatten it, and then like later you can unflatten it. This is the reason behind the notation of A is a matrix in R to the m times k. For example, in the 2x2 case, we can say that we could potentially forget that a matrix is 2x2 and say like, oh, this is a length 4 vector. So my point here is that we won't need this, like you don't really need the structure that the extra structure of a derivative of a matrix, or more generally a tensor, to compute derivatives. Like, because you at the end of the day, you're just doing things component wise. So like, like if you want to compute derivatives with respect to matrices, it's exactly the same thing. So we have like the trace of a function, the trace of a matrix, which is just the sum of the diagonal. Perhaps unsurprisingly, the gradient of this function resembles a lot the gradient of the sum function, which was all ones. Here we are just taking some part of the matrix and adding all those elements. So we know the gradient of adding all the elements, which is just a vector of all ones. And actually, like all the other elements outside the diagonal are not used in the function. So the derivative with respect to those is 0. You change those, the function doesn't change. So the gradient with the gradient of the trace function is just the identity matrix. Like a generalization, or actually the same thing with a different notation to the square norm that we had before. This is the square norm of a matrix, but in disguise, it's really exactly the same thing as the vector norm that we had before. We are just taking like one by one the elements, all the elements of the matrix, as we did before with the elements of the vector. We compute their squares and sum them all. The important thing here, and what's interesting, is that this notation with the trace of A transpose times X, what that is doing is, like, if you think for a moment about it, if you take the first column of A, the transpose makes it the first row, and you are computing a row back, you come in the first diagonal, the first element of the diagonal, you are computing the product of the first row, which is the first column, because it's transposed. So you are computing the vector, like the square norm of the first vector of the first column of the matrix. And then the second element of the diagonal, you are doing the same thing, second column transpose vector product with itself. So those are the elements of the diagonal, and we take the trace. So we get the square norm of a matrix. Again, like this norm is just something's called the Frobenius norm, but it's exactly the same norm as we had before. And of course, like if you can compute this using just the definition of the gradient, just going through each element and like saying like, oh, the derivative with respect to the first element is 2 times blah blah blah. But really, since we said like, oh, this function is actually the same as the function that we had before, and we know how to compute the gradient of the function that we had before, which was 2 times x or 2 times p for the vector, with the matrix, it's really exactly the same. So it's 2 times p. But again, you can also compute it like coordinate-wise. And then like later in the talk, we'll see like a third way to compute this derivative. So on maps, like I might have like some slips, and I might call some maps functions, but I'll try to do my best. So a map into Rk can be decomposed into k functions, and for map we define the Jacobian. The Jacobian is a k by n matrix, and the Jacobian, just the first row, it would be like the gradient of G1, the second row will be the gradient of G2, and so on. We'll see later on when we define a slightly more general version of these things. It's not quite right to say that the first row is the gradient of G, and when we give the slightly more general definition of a gradient. But like for now, that will do. What's interesting to note here is that these matrices were born to multiply vectors. That's what matrices are for, like matrix vector product. So a matrix vector product, what it is, it's a linear map. So it takes a vector from Rn to Rk. So if you think about this matrix as actually, I'm sorry for those are not here. So I don't know if they you want to see the board, but the idea is that like if you have a matrix here, and this is times
Mario,
yes.
If you write behind the podium, I could be.
Oh, here. Oh, nice. So the idea is that if you have a matrix that is n times k, like what you do here is you feed it a vector, a long vector of length n, and this gives you a vector of length k. So this really is like, if you think about this as a function that adds some vectors, it really goes in the same direction as G, meaning that like it's also a function that goes from Rn into Rk. And that's what we'll capitalize on later, really. But for now, this is just a function of partial derivatives. We know how to compute partial derivatives, as we said before, because these are partial derivatives of functions. So it's just derivatives of functions from the reals into the reals. So those are easy to compute. We could potentially compute this, and you can potentially compute this matrix. Note, as I said before, if this is for a map, but if f is a function, like then the gradient of f is just a transpose of the Jacobian of f. Like it's just the first row, but like we said that vectors are columns, so it's a transpose of the first row. Since this is centered, it must be because it's important. Like keep it in mind. So examples of Jacobians. The most simple, like one of the most simple functions from Rn to Rn is if you take a function from R to R and apply it coordinate-wise to a vector or a matrix or a tensor. In Python you have you can compute the exponential, or like term by term, the square root, the sigmoid, the hyper. So all these are like activation functions, or like they are like a good part. Almost all activation functions are at the end of the day element-wise maps. So what's the Jacobian of an element-wise map? Well, it turns out that the first coordinate just depends on the first coordinate. So when you compute the whole gradient, like you have the derivatives of the first function, which is in this case is g, with respect to all its entries, x1, xn. But like it just depends on x1. So all the other things are not the first coordinate are 0, and the first one is what? Well, the derivative. So it's just the derivative of the function g hat as a function from the reals into the reals. Same happens with the second. The second function, just d2, just depends on x2 and so on. So it's a point here is that the Jacobian is diagonal. It's a diagonal matrix. And it's just it may be represented as the computing the derivatives of the vector given by the derivatives of g hat, which is again just a function from the reals into the reals. So if we think about it as Jacobian vector products, that we'll talk more about later, but like this idea of like the Jacobian is made to be multiplied to multiply vectors on the right. So we do a Jacobian vector product. You think about it, a diagonal matrix times a vector is just a pointwise product. Like you just take the vector in the diagonal and which here I call G prime, which is just the vector with components G hat prime P1, G hat prime P2, etc. And you do the element wise product with D. And that's what I denoted with an asterisk there, because it's the notation that we use in PyTorch. You just put an asterisk, and that's a multiplication. So basically, we can compute Jacobian vector products by computing this, but by basically we have, for example, the sine function. The derivative would be the cosine. So we're gonna here to compute the Jacobian vector product, we compute the cosine evaluated at the point P times B. So that would be the Jacobian vector product. So it's very easy to compute. Slightly less trivial function, matrix multiplication. Matrix multiplication, if we have a fixed matrix A, that's 2 by 2, we can map another 2 by 2 matrix X onto the product X times A. Coordinate-wise, you get this. It's just the usual formula for the matrix multiplication. May have made some mistake there, I admit. But the point here is that, how do you compute the Jacobian of this? Well, we said that, this if something depends on a matrix, it's the same thing as depending on a vector. Only need to flatten it, then compute the derivatives. So here the Jacobian would be, since we have 4, this is a function from R 2 by 2 into R 2 by 2. So the Jacobian will be a matrix from R4 times, that is 4 by 4, so 16 entries. And you would need to compute the partial derivatives of that. It is a real pain. I recommend people to do it once so that they feel comfortable that they can do it. It will take 15 minutes, and that's it. And you do it, and you never do it again in your life because it's just terrible. But that's that. But the point is that it can be done. There's nothing fancy going on here. So what you can do also is that you can do some computations. You flatten the matrix A. If we want to compute the Jacobian vector product, what we do is we pick a matrix E, we flatten it into a vector, we compute the Jacobian, which is a 4 by 4 matrix. The E that we flatten is a vector of length 4, and then we compute the matrix vector product. It gives us a product of length 4, and then we unflatten it. And after doing all that, we see that the Jacobian vector product is a matrix. It can be, you get a vector and you unflatten it, and then you look at the vector and you're like, oh, but this is actually a matrix multiplication. But after doing all this, that seems completely unrelated. There's no reason, apparently, a priori, there is no reason why that matrix vector product and the result of that, when you unflatten it, it should factor out, it should be represented as a matrix multiplication. There's a priori no reason. But the fact is that it can be done. And the second part of the talk is going to talk about that, the reasons why this is like that. And then when you understand the reasons, you are like, oh, it's this way because there's no other way that it could be. There's some very geometric intuition for why this formula is like that. But you can also compute it algebraically. It's painful, but you can do it. And the point is that, all right, now let's use the high-level tools not to have to go through that ordeal. So yeah, since there's structure, there must be another way. This is literally the principle behind all mathematics. If you find some structure, there must be a reason for that structure to be there. So, a couple more things. The chain rule basically says that we have the Jacobian of a composition of two functions that can be composed. Then the Jacobian of the two functions is just the matrix multiplication of the two Jacobians. Like that's all that the chain rule says. Now the chain rule allows us to compute the gradient of a composition. So we have that the gradient of a composition is that we saw that like it will have a function f, and we pre-compose it with a map G. We remember that thing that said that the Jacobian of a function is the transpose of the the gradient of a function is the transpose of the Jacobian. So we apply the chain. So here we apply the chain rule, and then we use that the transpose of, like, these are just matrix multiplication. So the transpose of two matrices is the multiplication of the matrix of the transposes in the reversed order. And here we have already the transpose of the Jacobian of f, and f is a function, so that's the gradient. So basically, this gives us the formula for how to compute the gradient of a composition of two functions. So what this says is that if you are interested in gradients, and we are, because like that's the premise of this talk, we are in the business of computing multiplications of the transpose of the Jacobian times a vector. That is the quantity that we are interested in, and that's the quantity that we'll revisit later on. And we'll give a more abstract definition of what's the transpose of a matrix, without really saying like, oh, you take the coordinates and you invert them. We're going to give a more abstract definition of the transpose of a matrix, which by itself I think is quite interesting. But yeah. So last thing before really going into the meat of the talk, linear maps. So we say that a map is linear. A map between Rn and Rk is linear if it, I mean, like mathematically you would say it commutes with the multiplication by a scalar and it commutes with the addition. So it doesn't matter if you first add two vectors and then apply the map, or if you first apply the map and then add the two vectors. So that's what the first formula is saying. That, and it doesn't matter if you multiply by a scalar first and then apply the map, or apply the map first and then multiply by a scalar. The second condition is usually said that is like you usually say that the scalars come out of the operation. You know, like you just can pull out the scalars. So examples of linear maps. Perhaps the simplest example would be the identity. Like if you don't do anything and add two things, is the same as adding two things and then sitting down and not doing anything. But like beyond the simplest example, well, the diagonal, like basically taking the diagonal of a matrix and just considering that as a vector, that is linear. You know, like a moment of thought, like basically tells you that like if you add two matrices and then you take out the diagonal of the two matrices as a vector, or if you take out the two diagonals and add them, that's exactly the same thing. And then exactly the same with multiplying by a scalar. More generally, advanced indexing, so pulling out elements out of a matrix or a tensor and like putting it in a new tensor, that's also linear. Like all those with like, you know, however you want to pick out elements from a matrix or a tensor and like putting them in a new tensor, all those things are linear for exactly the same reason as before. Torch sum, torch mean. So yes.
I have a question about previous step.
Yeah, absolutely.
Is there some like why do we see these transposes, right?
Yeah.
Why do we not define the gradient itself as a transpose? We don't have to.
Yeah. So the question is why don't we define just the gradient as a transpose of the Jacobian? We could certainly do that, but we'll see later on that there is a better definition of a gradient, like more abstract. So the truth is that these things, the way they were invented, like, you know, you define these things like this was from the, I don't know, 17th century or something, or 18th century, you know, like you define things in a somewhat sloppy way, and then like you formalize them, and at some point you generalize them. And then at some point, the things that generalize well, you take them as the definitions, and you say that all these things follow from that. So what we're going to see later is the more general definition. And like with the more general definition, I mean that this works for, again, like differential geometry. When you have manifolds, you can also define gradients, and you can define all this stuff. And also, like, you can also define all this stuff when you have vector spaces that are of infinite dimensions in functional analysis and all these things. So you could certainly do that, but we're going to have a definition that's arguably even better than that. Certainly, you could say that, yes, but yeah. Also in the talk, for the sake of exposition, I wanted to go from simpler to more difficult. So it started with gradient, then going to Jacobian. Yeah. So linear things, taking the sum of vectors, as we saw before, it's a linear thing. Same thing with taking the mean of a vector of fixed size, because you are just like doing just multiplying by constants, so that's also linear. Yeah, good stuff. All the things are linear. Taking the transpose of a matrix is linear, because you are, again, like it's like advanced indexing, really. You are just reshuffling the elements. It's all good. Taking the trace is a composition of diagonal and sum, and the composition of linear functions is again linear. So another thing that is linear is if we fix A and we compute the multiplication by a fixed matrix, that is also linear. So matrix multiplication is linear. We said that, like, the prototypical example of a linear function is multiplying a vector by a matrix. So if you fix a matrix, multiplication by a matrix vector product, that is linear on the vector, also on the matrix. But yeah. So these are examples of linear maps, and like what we are going to do later in the talk is, like, we are going to basically simplify all this business of computing Jacobians and all this stuff to identifying linear maps, because we will see that computing the Jacobian or something that smells like the Jacobian of a linear map is very, very easy. So we'll basically get into and we saw that computing Jacobians for element-wise functions is also very easy. So we'll be in the business of, like, we'll simplify all this stuff of computing derivatives as computing derivatives of element-wise, as decomposing a complex function into element-wise operations and linear operations. And if we're able to do that, and we are able to compute the derivatives of a linear operator, which will be very easy. And I say linear operator, linear map independent is the same thing. So if we are able to compute the derivative of a linear map and the derivative of a coordinate-wise, element-wise map, then we use a chain rule and we are golden. So that's sort of going to be the drill that we are going to be doing here. So also, function may be bilinear. That is, a function that takes two arguments is bilinear if, when you fix the first argument, when you fix the second argument, the function is linear in the first argument for any second argument, and you fix the first argument, it's linear on the second argument. So basically, you have to see that, you know, like this sort of like checking that family of functions is linear. Bilinear functions are very similar to those above. For example, like the simplest bilinear function is just multiplication of two numbers. If you fix one of the numbers, it's clearly the multiplying by a constant is linear on the first argument, and same multiplying by a constant. It's commutative. More generally, like point-wise product, like of two tensors, is linear. Like it's bilinear. Sorry. Matrix vector, matrix product, matmul in PyTorch, and that notation for matmul with the at. All those things are bilinear functions. So if you fix one matrix, as we said before, multiplying by a fixed matrix is linear in the other variable, and multiplying by another matrix linear in the first variable. So all these things are bilinear functions. Slightly less trivial example, but when you think about it, is easy to see using this definition above. CNNs are bilinear functions in the input and the kernel. It's like all you're doing in a CNN, coordinate-wise, is like you are like doing element-wise multiplication by kernel and adding all those things. So that is linear because like it's just a composition of two linear functions, and then like that is like that in every component. So that is a bilinear function, really. Like if it's not obvious, like just like play with the definition of a CNN. And the idea is that like if you know that this is bilinear, and we know how to do things, how to compute things for bilinear functions, even if computing like the formula, the first time that you see the formula of a CNN, you are like, oh, fuck's sake, what's this? There's so many indices, like you just don't, don't understand what's going on there. Yes?
This is without any nonlinearity.
Oh yeah, absolutely, absolutely. This is just like the CNN, like plain CNN. Then like, again, like we want to decompose things as much as possible. Then we will use a chain rule to put them all together. So CNNs are bilinear. Slightly more non-trivial example of a bilinear function. A little warning, a bilinear function that takes two arguments is not a linear function if we concatenate the two arguments and see it as a function from R. Oh, you kind of see that there. That's annoying. So what this says is that like if you put this together, so like if you consider it as a function from R n times m into Rk, it's not linear because like the simplest counterexample is literally the simplest bilinear function, product of two numbers. X squared is not linear, let's say. So like x times y is a bilinear function, as we mentioned, but it's clearly not a linear function when seen as a function from R2 into R. So because like the second rule just basically A comes out with an A square, when you multiply, like when it comes out from the T with as A square, not as A. So just a small thing. All right, now into the slightly more abstract stuff. Like again, we're going to be looking at exactly the same things that we saw before, exactly the same definitions, exactly the same everything, but we're just going to change the notation to address, like basically underline the things that are important, stress the things that are important, and like leave out all the detailed details, like the fact that linear functions are like maybe represented as a matrix vector product. If you have studied like linear algebra, like that's the first result that you see. And if you think about some of the other functions as matrix vector product, can be like very confusing to figure out what's a matrix, but it's very clear that those other functions are linear or bilinear, as we said. In any case, like we are going to shift the perspective, and we are just going to use the definition of a linear map, and we are going to start looking at matrix Jacobian vector products as linear maps, and we'll capitalize on that. So first of all, what's this? All right, so this is a Taylor approximation. This says that it's a Taylor approximation in higher dimensions, but it's exactly the same thing as doing the Taylor approximation coordinates wise. Like if you think about this formula is if you think about it for a function from the real numbers into the real numbers, all this says is that a first order Taylor approximation of a function at a point is just the best affine function so it's a tangent function so it's starts at point GP plus a linear term in X, a term that is linear in X. So this is exactly the same thing, but with more coordinates. Yeah, again, Taylor approximation, not interesting. Well, really very interesting because like it's what we'll use to generalize all this. So that formula, that's approximate symbol that doesn't mean anything really in maths, can be formalized as this. You basically say that these things are equal up to an error term that grows higher than linearly. If you think about it, the Taylor series of this, like this is just we have truncated the Taylor series at size at something of a degree 1. So basically, what we have left is that we have left things are quadratic, cubic, and so on. So basically, what this notation says with the little o says that there's terms that grow faster than the norm of v, that grow faster than linear. More formally, the definition of the second line is literally this definition. That, you know, like I could have started with this definition, but it's a bit daunting. You know, first time that you see this limit, you're like, oh, where's all this coming from? But all this is saying is that the derivative is a first order approximation. It's a linear first order approximation to G. We saw that it's linear because it's a matrix vector product, so it's certainly linear. But so what we see here is that all this formula is saying is that if we move all those like the GP plus the Jacobian to the left of the equality, and we divide by the norm of V, and we take the limit as the norm of V tends to 0. So we approach P. Like in that formula, when V is 0, we just have we are tending towards P. So what this is saying is that all the other terms of the Taylor approximation are just growing much larger, like are tending to 0 much faster than this part of the Taylor approximation. So this is like basically now what we're going to do is we are going to take this as the definition of the Jacobian. Like this thing that we saw that the Jacobian is a solution for this, and like basically all this definition is saying is that we define the differential of a map as the linear function d of g such that blah blah blah. What is that function? Well, that function is the Jacobian vector product, because we literally built this starting from the Jacobian vector product and the Taylor approximation. And we said like, oh, the Taylor approximation says this, and then we rearrange everything and we get to this limit. So basically, this is the definition of the Jacobian vector product. But what we are saying here with this notation, with the differential of g and so on, what this says is that this is a linear function. And like we are going to stress like this is a linear function in V. So, you know, we see here at the very top that we take d of x, that's a linear function. So it's not a function that's linear on x, it's linear on V. And this notation will stress that. Like this notation, we'll forget that it's a matrix, we'll just think of it as a linear function. We define also that computing forward mode AD, like I don't know, like how many of you have heard and like knew the definition of forward mode AD? Not very many, or fair enough. It's something that's used, like the applications of forward mode AD is to compute faster like Hessians of functions, second order approximations in like PyTorch, and in particular JAX was the first one that started using all this stuff. And basically like the idea of like introducing these things now is that you won't know the applications now, but if you know the definitions and you go read the applications, you already know the concept. So you'll understand better, and like you'll be able to easily understand, you know, what's what, and you won't need to first understand, all right, what's this forward mode AD, and then like, all right, what are the applications? So computing forward mode AD, it's computing the differential of a function at a point x evaluated at a vector b. So all this is saying is that computing forward mode AD in terms of the Jacobian, it's computing Jacobian vector products. This is just a different notation for Jacobian vector products that stresses other things. But computing forward mode AD is computing Jacobian vector products, or in our notation, computing the differential of the map evaluated at a point at a vector. It's also interesting to see that what this notation says, it goes from matrices to functions, from matrices to linear maps. So here we can see that if we have a function g if we have function g that goes from Rn to Rk, the differential of g, also evaluated at that point, goes also from Rn to Rk. So it goes in the same direction as g. And even more, like the way we should think about this is that the differential, let me close that. So the differential of g is a linearization of the function. So you have a function that is like that, and you choose a point, you choose the best linear approximation to the function on that point. The similar way that we were doing this, only that this is an affine approximation, but the affine approximation given the linear function is just adding the point f evaluated at the point. So as we saw before, like in the Taylor approximation, we have a linear part, and this is like an affine function, really. But so the Jacobian is the linearization of a function in the sense that it's a linear part of the best affine approximation. And the affine approximation, again, is just, like the tangent, although slightly more general than the tangent, but like the tangent of the function of, the best linear approximation. Well, so definition, just left it here for you to remember. So linear maps. So then, like, what is the differential of a linear map? Well, what's the best approximation to something that's already linear? The best linear approximation to something that's already linear, but itself. There's nothing to do there. Now, the proof with this notation is very easy, really. Because it must be easy, because we have defined the differential as the best linear approximation. So, the best linear approximation to something that's already linear must be itself. So we just plug in the definition of the differential, which is just itself, here in the first, and we just use linearity, everything cancels, boom. There's nothing to do, because we have defined everything, there is loads of geometric intuition behind, and that's basically the good way of thinking about these things as the linear approximation. And then when you understand that, and you have all the toolbox of what is linear and what is bilinear and things like that, then you are basically set to go. There's no need to compute the partial derivatives, and there's nothing of that. So now a few things. Since we are now talking about linear maps, but at the end of the day, they are just maps. We can compose them, and it turns out that the chain rule may be just rewritten as the differential of the composition is equal to the composition of the differentials, which is a very, very clean way of writing the chain rule. Before, we were mixing maps and the different, the Jacobian of the composition, and then that would come out as a matrix multiplication. But we think about the Jacobian vector product, where we are doing matrix multiplication and factoring out, having two matrix multiplied. If we apply a vector on the right, that's applying first the first matrix and then the second matrix, because that's, they are multiplied. So that's what this is saying. This is saying the differential, more abstract terms, the differential commutes with the composition. And this is actually extremely, it's the basis of differential geometry. Differential geometry works because this equality actually happens. But it also makes a lot of sense, if we would have one thing onto one space and then another thing onto another space, the best approximation of the final thing is getting the best first approximation and then compose it with the best approximation of the second part. It's intuitive, really. And basically what this notation stresses is these intuitive things and these more geometric things, perhaps. Technical thing that is a bit of a pain the first time that you read it, but then this is a mouthful, really. This is just, but it is very simple once you understand what this is saying. What this is saying is that it will have a function with two variables, with two input variables, the derivative of like the differential of the whole thing is computed derivative with respect to the first variable fixed in the second one, plus the derivative of the second variable fixed in the first one. That is what this is saying with quite a bit of notation, really. So, you know, we define g1 of x as the function g with the first variable fixed to be x, and then we define g2 comma y as evaluating the second variable of g to be y, and then getting, you know, this in computer science is called carrying and all that stuff. Yes?
So the last time we had chain rule, right? We had like transposes in the Jacobian. What happened to those here?
So the proof of this is like we can prove it using Jacobians. Like when you
like a few steps ago when you introduced the chain rule before.
Yes.
That time we had like transposes in the Jacobian.
So the Jacobian, so yes and no. So the let's go back. So this is a chain rule, so there's no transposes there yet, because like well, we compute the Jacobian vector product. The differential is the Jacobian vector product. So here, what this is saying is we computing the Jacobian vector product of the composition is computing the Jacobian of g of x times v, and then you get another vector, and then you compute the Jacobian of h at that point times the vector that we had before. So
yeah, this makes.
All right, cool.
But the next one?
Oh, we are not there yet. Like that's for gradients and stuff, and like we haven't generalized what a gradient is. Like we haven't talked about gradients in this new framework. We have just talked about Jacobian vector product. No, we don't know what's a transpose yet.
Okay.
Yeah, and we will define that, but like not yet.
Okay.
Yeah, thank you. So again, this is basically like rearrange, like it's basically like a generalization of partial derivatives, if you want. Like partial derivatives is computing the derivative with respect to one element fixing all the other elements. Here we are computing the Jacobian with respect to one element fixing, like, well, with respect to like part of the input fixing like the second part of the input. And then we get the Jacobian of G2, like so fixing the second part of the input. And then, so this is like this notation is just block notation, like, you know, just two matrices that form a larger matrix. So the proof is straightforward using matrices. And again, like if you need to prove things, like there's no shame in proving them using matrices, really. These things are the same, and like you should be able to use whichever tool feels comfortable or feels right for each moment. And the more you use these tools, the better will be your understanding of what's the right tool. It's exactly the same as programming. Like if any of you programs in C++, you know that, or like in a like in anything other than Python, perhaps. Like there's so very many things. There's so many very ways of doing one thing. And like being a good programmer is being able to pick up the right tool for the right moment. So this is exactly the same thing, you know, like, yes, we have all this framework, but like, do we need to compute stuff using matrices? We do, and compute stuff using matrices. So, all right, now that we have all this, yes?
I didn't really get the notation, but why do you have 2, y?
So what this is saying is that if you have, let's erase this. Oh, it's not very good. Okay. What this is saying is that if you want to compute the derivative of g of x, y with x, y real numbers, for example, and you want to compute the differential of g at the point 3, 2, right? And this will depend on v1, v2, which are also real numbers. This is the same as computing the derivative of, so it's computing the derivative of the function blank, 2. And so, you know, like the derivative with respect to x of this function plus the derivative of with respect to y of g3. Yeah, sorry, getting that.
Yeah.
But,
yeah.
So this is all this is saying, and like what you can do, like you can go to the definition of the Jacobian, like write the Jacobian for a 2-variable function or a 4-variable function and split it in 2 variables of 2, and just convince yourself that this is right. But like it might take like a minute of thinking about this, and then at some point you're like, all right, yeah. It's not difficult, but yeah, it might not be obvious at first. So now we can capitalize on this short proof that we had for linear functions. So of computing the differential of linear functions is easy. So we knew that computing the matrix computing the matrix product with a fixed matrix, the matrix multiplication, with a fixed matrix is linear. So computing the differential of this function map is just evaluating it at the vector that we are computing its differential at. So if we are computing the differential at the vector e, well, I'm calling matrix a vector really, because like there's this thing that like in my head, like matrices are things that take one, that are linear operators, and then these things are vectors because like even when you think about it, like you think about it as an operator takes a vector onto a vector. So d of g is a Jacobian matrix that defines a linear map, and the linear map takes vectors onto vectors. So even though this is a matrix, like can be thought of as a vector when you flatten it. But what? So the differential of g at e is just g of e. So we just evaluate, and we have computed a differential. So remember, this is the formula that I said at the beginning that you can compute using the Jacobian vector product. This is the example of the matrix multiplication from the beginning by a fixed matrix. And you can do it using the Jacobian, but it's a pain. But now it's obvious why this formula is like this. It's like this because it's linear, and the Jacobian vector product is the best linear approximation, and that's it. And it's really very easy to remember. Like it's like this because it cannot be any other way. If we have like a general matrix multiplication of 2 matrices, then we can use this thing of like having multiple inputs. So the differential of this thing evaluated at the matrix x, y on the vectors e1, e2 is equal to the derivative with respect to the first one fixing the second one. And since it's bilinear, like that is, when you fix the second one, it's linear on the first variable. So we can apply the little proposition that we have for the differential of linear maps, and then plus exactly the same reasoning on the second variable. So we have computed the differential of this linear map. This bilinear map. Interestingly enough, this also applies for any other bilinear map. So if you want to compute the differential, or in the machine learning setting, the forward AD of the CNN, which is really a lot, because the CNN is not easy to implement and so on. Like you're like, all right, how do you? Yeah, it just follows like this. It's just the differential of the input with the kernel fix plus the differential of the kernel with the input fix is linear in each of those. So we can apply that, and so you can compute the forward AD or the differential of a CNN just with 2 CNN evaluations, for example. Slightly more difficult, or like slightly less trivial example, the 2 norm, which is the square root of a vector product. Like if we denote the vector product as x transpose times y, and this is just a slightly different notation. And we are going to introduce this notation because now in a second we'll define formally what a vector product is, like more generally. But like for now, like it's just x transpose times y, and we can define f to be like the square root of the scalar product or sorry, vector product of x with itself. So the differential of f. How do we compute the differential of f? So we first of all, this is clearly the composition of two functions. We are first applying the scalar product of x with itself, or inner product, or vector product, or any of those things. I'll say any of those names for this, and then we are applying the square root. So that is then what we do is that we compute we use the chain rule. So the differential of f at a point x evaluated at a vector b. Sorry, let me start. So the differential of f at a point x evaluated at a vector b is the differential of the square root evaluated at the point x comma x. So you remember the differential, the chain rule must be like you have to evaluate the second map on the point on the image of the first map, composed with a differential of this thing evaluated at the point x, and that goes to b. So this first part, it's a linear map. It's a bilinear map. So this is given by, sorry, let's not get ahead of ourselves, is f comma e. Sorry, we are using, what am I using? I'm using b, sorry. X comma b plus b comma x. But this is symmetric. Like the inner product is symmetric. So x comma, so the vector or the inner product of x and y is the same as that of y and x. So this is just 2 times x comma b. And then the differential of the square root, this is just the derivative. Like, this is just the normal derivative. So like that is 1 over 2 times this, x comma x. Sorry. So, sorry, it's 2 times like the square root of what you're evaluating. I don't know how to compute simple derivatives. So this is just the 2 norm of x. And then if we multiply everything together, because that's a composition here. So these 2 simplifies it with these 2. And then we get that, basically we get that formula. Because we have like, at the top we have x comma b, and these 2 simplified with these 2 divided by the norm of x. So we get that formula. And we really haven't done anything. We have just like decomposed things into simpler things, and we know how to compute the derivative of simpler things, and like there's no partial derivatives which are pain, and like much more error promises. Now onto the transpose. Like how do we generalize all this transpose business? We need to add a small piece of linear algebra, like a very small piece of linear algebra, which is vector products. So the definition of a vector product, well, first of all, let me leave it like that. So a vector product is it's a map. It's a bilinear map, and we already saw the definition of a bilinear map. It's symmetric, and it's positive definite. So we remember that the x comma x, like the square root of x comma x, is the norm of x. So x comma x, so the vector product of x with itself is the square of the norm, and since it's a square, it better be positive. So it's positive definite, and then it's symmetric in the sense that x comma y is y comma x. the canonical vector product is X transpose times Y, as we have already used. But there's other vector products just for you to like have a taste of other sorts of vector products. It's not, we are not going to use them, but just for you to have a look at how, you know, what are other examples of vector products. So we have a symmetric positive definite matrix, then that is, you know, like we can multiply in the middle by the symmetric positive definite matrix, and that is certainly symmetric because you know, when you compute, if you compute the transpose of that other thing, basically, of that thing, which is a scalar, so the transpose of a scalar is scalar, it's itself. Since A is symmetric, then the whole thing is symmetric. Certainly bilinear, and it's positive definite because it's symmetric positive definite. And like an easy proof for why everything works is you use Cholesky or the SPD, and that's it. But not very important. Again, other example. This is important, right? Like this is again something called the Frobenius vector product, and it's another way of writing the canonical vector product on Rn times k. So Rn times k, it's just Rn. Only that, you know, like if we flatten everything, like we see like Rn times k, as we said at the very, very beginning, as Rn. And it turns out that these two things, like if you compute the trace of the X transpose times Y, it's the same thing as flattening the matrices and computing the canonical vector product. It's exactly the same thing as what we saw at the beginning with the trace of X transpose times X. The proof is exactly the same, but I would very much encourage you to like really convince yourself that all this is doing like a coordinate-wise multiplication of x11 times y11 plus x12 times y12 and so on, and adding all of those. So it's like a coordinate-wise multiplication and then a sum. Like that's what this is doing, really. But this notation is very useful, as we'll see in a second, because like we work with things that are very amenable from a perspective of mathematics. We are working with the trace and the transpose that are really very amenable, yeah. And then another example of vector product on matrices, which is less general than this one, but I'm not going to get into it, like just for you guys to have like another example of other vector products. So now into where we are, like, all right, so for now, just for simplicity, when we use a vector product, we will mean X transpose Y for vectors and the transpose of X transpose Y, sorry, the trace of X transpose Y for matrices, which again are two ways of writing exactly the same thing. But yeah, like they are exactly the same thing, but they are just, the transpose is just a convenient way of writing that when X and Y have the structure of a matrix. And also we recall that the differential of a function is just a function that goes from Rn onto R. Like it's a map, but like since it's a function, the codomain is Rk with k equals 1, so it goes into R. So now, gradient, abstract definition of a gradient. So what's a gradient? The gradient is the vector in Rn such that the differential, such that the vector times any other vector v, is equal to the differential of f evaluated at v. Things to note here, the types match of these functions. Like we have a linear function on the v variable on the left, and we have, since the vector product is linear, it's bilinear, in particular it's linear on the second variable, we have a linear function on the right. So, all right, fair enough. And what this is saying is that like, if you find a vector such that you can represent the differential of a function in this way, then you are, like that's a gradient. Now, think about it for a second using the perspective of Jacobians and matrices and all that. what is this saying really? Well, in the case of a matrix, the Jacobian of a matrix is just the transpose of the gradient, meaning that it is a row, like a row, because it's not vector, it's a row thing with the partial derivatives. When we go, and that's the differential, and then the differential evaluated at a point V is that it's that product, that thing, that row thing, which is a matrix really, but it's a row matrix, multiplied by the vector V. So that's what this part is saying. And what this is saying, like this, sorry, let me use the mouse. So what the second part is saying is that we have that the scalar product or the inner product is X transpose Y. So we have a V, and then we have like on the left we had this row matrix, but what this is doing effectively is like saying that, oh, now we have a vector, we want a vector, and the vector is going to be the column vector, because then if we take the definition of the gradient from the very, very beginning, from the first slide, we transpose it and then do the vector product or matrix vector, only that the matrix is a row matrix, then we get the differential, the Jacobian vector product. So this is an abstract definition of all the things that we saw before. But like in reality, you know, this is just the things that we saw before in disguise. Now, this is slightly more general, because here we are saying, all right, let's say that this vector product is X transpose times Y. But what this is saying is that the gradient, like really, we could use any other vector product. Like we don't really need to use that vector product. We could use one of the other fancy ones. And actually, this is very important in differential geometry, because you have metrics and you have like, it's not clear what the vector product or the metric on a manifold is, and you can use different metrics and so on. Like this is just like the deviation for those of you that may know a little bit about these things. But the interesting thing about this part is that it doesn't talk about coordinates. Like this can be done in infinite dimensions. Like you have a Hilbert space, you can also do the same in infinite dimensions. And it's also going to be very useful for us to compute derivatives, as we will see in a second. So, example, well, the first example that we saw that we have the, since f is linear, we know how to compute the differential of f. Like here, we have just the sum of n numbers, the sum of all the vectors, sorry, of all the elements of a vector. So we can write that using the canonical vector product, the X transpose Y, as the vector of all ones times V. You have like the vector of all ones times itself, and sum all the things. So that's equal to the differential of f. So the gradient is just the vector of all ones, as we had computed at the beginning. Yeah. Something that's interesting is that like the gradient depends on the choice. Like this is not important really, but it's a good thing to know if you are like going to dig deeper and deeper into this stuff. And is that the gradient of a function depends on the choice of inner product. Here we are choosing this inner product, but we may choose a different inner product. So it depends on that. The differential doesn't, but the gradient does. This is again important in like more general context. This small thing. That's it will not be necessary for what we're doing here. So the gradient of the 2 norm. So the differential of this function is what we computed before. It's just x times v divided by the 2 norm of x, which can be written because of the linearity, because it's the inner product is bilinear, so you can put like 1 over the norm of x is just a scalar, so it can be moved into the first component of the inner product. So the gradient of f is just the left-hand side of that, so x divided by the norm of x. the same thing with the other, like more scary looking norm, really. Like we are like here, we are just using that the trace of blah, blah, blah is bilinear. And like we're just using that it's a linear, like that it's an inner product. And really the only thing that we used is that it's linear on the first variable so that we can compute the differential using the formula. And then it's also linear on the second variable so that we can pull that in, and that will be the gradient of the matrix of the function. So the gradient of f is x divided by the 2 norm of x. Again, these things, I think that they are not necessarily too difficult, but like see that you are getting like you are taking like larger steps, really, because like you know what are the things that you can use, and you just use those, and it's a matter of like composing those and playing around with those until you get to the result. And now the last thing that we need is like to compute. All right, so what's the transpose of the Jacobian, which has the last piece in the puzzle that we're missing. So the transpose of the Jacobian, like we want to compute the gradient of the composition. Well, we have we have a function and a map. We have the differential of the composition is the composition of the differentials, and then with we represent this composition of differentials like changing the definition, changing the differential of f into its gradient form. So it's the inner product of the gradient of f times the differential of g. And to compute the gradient of the differential, we would like to solve for v in this like rightmost expression. So we'd like to move the differential of g to the left-hand side of the inner product. So turns out that this is called the adjoint of a linear map. The adjoint of a linear map, and it can be defined in general for arbitrary vector products on Rn and Rk, and this again generalizes to manifolds and it generalizes to Hilbert spaces. So we define the linear map, the adjoint, as the map T star, the linear map T star, such that it basically like moves onto the from the left hand side onto the right hand side, or like the right hand side to the left hand side, because it's symmetric, the inner product. So it's note first of all that it's a map that goes in the opposite direction as T. If D goes from Rn to Rk, this goes to the adjoint goes from Rk to Rn, so it goes in the opposite direction. It is linear in the sense of what we discussed before, with that it commutes with the addition and the multiplication by scalars, and basically it goes, it basically allows us to solve for v in that equation above, because like if we basically apply, we have that d of g here is a linear function, and if we compute the adjoint of the differential of g, that basically moves the d of g to the left-hand side, and that will be the gradient of a composition. So basically, what that says is that the proposition gradient of a composition is given by the computing the adjoints of the differential. Now, we already developed it. Yeah, is that?
I kind of didn't get this solved for me.
Oh, so what you want to do is, what you would like to do is to have some because like the definition of the gradient is like it's the vector that you can put on the left-hand side, such that that vector times b is the same as the differential of the function, right? So what we would like here, we have already moved the f to the right-hand side, saying like, all right, we have the gradient of f, if we know how to compute the gradient. Now with g, like we have like that g on the right-hand side, and we would like to find something, that basically leaves just v on the right-hand side and then moves whatever information from g to the other side. So, so this is basically what we would like to do, and the differential. So basically, we need, now all we need to do is to see how to compute. Well, first of all, how is it related to transposes? Like I said that this is a generalization of the transpose of the Jacobian, and what this example shows is that in fact it is. So if we choose the canonical vector products, although here this is, this can be done with arbitrary vector products, but it's not important. With a canonical vector product of like x transpose times y, if we fix a matrix A, then and we have the linear map A times B for a fixed matrix A, then we have that A times B, so applying T on the left, multiplied by W, is by definition, well, here we're just writing it down with the definition of the canonical vector product. Here we are applying the transposes, so the transposes like flip the order of B times A, and then this can be rewritten as B, comma, A transpose W. So what we are doing here, this is a generalization of the transpose by the terms of linear algebra. Like here, like we are like moving away from matrices, and we are just talking about linear maps, and this is a generalization of the transpose, this adjoint. So like, and for the last slide, really like let's compute a few of this. And here I just put in like a few like well-known identities for the trace, because we are going to use a trace. When we use matrices, we have that the vector product can be written as a transpose, the trace of the x transpose times y. So the trace is invariant under circular permutations, and the trace of A is certainly equal to the trace of A transpose. So let's compute the gradient of a matrix multiplication. So if we fix a matrix A, and then we have a matrix multiplication by a fixed matrix, then we have the differential. The formula for the differential follows from the proposition. So the way to compute Jacobian vector, the way to compute the adjoint of the differential is we pick a fresh vector, like we, in this case, a matrix. We pick a matrix G, we compute the scalar product, and we try to solve for, in this case, we are calling it E. Like we try to leave E on the right-hand side. So we're using the formulas above. So we just first the first equality is just that the trace, like it's just the definition of this vector product. Then we are using that the trace is invariant under circular permutations. And then here we are just grouping the G and A transpose under the same transpose. And then this is again like the inner product on matrices. Only on the left-hand side we have G A transpose. So that is the gradient, or better, like if that is like that's how you compute the adjoint of the differential of matrix multiplication by fixed matrix. And like this basically is a map that takes G, and I'm calling it G, like large G, because it's usually like if you think in neural networks, G is the output, is a gradient with respect to the outputs of the function, and in backpropagation you get the gradient with respect to the inputs. So this is what this is doing, like backpropagation. It's called backpropagation because it goes back, and the going back comes from the fact that the adjoint of a linear map goes in the opposite direction to the original linear map, as we saw in the definition. So here are a few other examples that are useful, and like I would very much encourage you to like work this out, because they follow in this exact same way from these formulas. But yeah, a few examples. So just to sum up, what have we covered? Computing forward DD and backward DD for an element-wise map is easy. The Jacobian is just like the pointwise multiplication by the derivative of the element of the map from the real numbers to the real numbers, and then also computing the transpose of that. Since the Jacobian is diagonal, the transpose is exactly the same thing. So the transpose of the Jacobian of an element-wise map is the same as the transpose of the Jacobian is equal to the Jacobian. So there's nothing to do there. Like if we know how to compute Jacobian vector products, we know how to compute the adjoint and blah blah blah. So computing forward AD for linear and bilinear maps is easy. We just have that very neat proposition that we've been milking throughout the whole class. Computing the backward AD for a map, I basically account the way that you do it in practice is to compute the differential. You take an arbitrary vector W and you plug in the formula for the differential that you have already computed, and then solve for B in that expression. And what you'll get on the other side, on the left-hand side or right-hand side, whatever you choose, that's it. That's the adjoint of this. And this is a claim, or you can, like using these rules, I assure you that you can compute the derivative of everything, because I'm literally the maintainer of those things in PyTorch, and I can tell you that you can do anything else. So things that we haven't covered. We haven't talked about derivatives with respect to complex numbers. Like you can have matrices with complex numbers. And the claim here is that it's really exactly the same thing. The complex structure doesn't change anything. Of course, you have to be a bit familiar with complex numbers and not be scared by what's a conjugate and all this stuff. But the thing is that we are just using, it's the same theory as before goes through, because a complex number is just two real numbers. So a complex matrix is just two real matrices or a larger real matrix. So in the same way that at the beginning we said all right, we don't care about matrices, vectors are enough. In this case, we don't care about complex numbers, real numbers are enough. So the only thing that changes is that, well, first of all, the differential of a function is the same. Like all this reasoning doesn't affect complex numbers. It does, the only thing that changes is that you have to realize that this is another way to write, yet another way of writing the canonical vector product for complex matrices. So basically what you would get here, if you work out what that formula is component-wise, basically gives you that is the product of the real, you go to the first component, and is the product of the real parts of each of the components of the first element of the two matrices, plus the product of the imaginary parts of the first element of the matrix of the two matrices, plus blah 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 with all the other elements. And then when you use this vector product in the computations to compute the adjoints and to compute the gradients, well, you get the complex, the formulas, the equivalent formulas for complex matrices. The formulas are very similar, but basically what you end up having is that you have to sprinkle a few conjugates here and there. But again, you have to prove these things, but once you see the pattern, you are all right, this is literally the same thing as in the real case. The other thing that we have left out is some very cool stuff that is derivatives of inverse maps. You have a linear solver, which is the inverse map of multiplying two matrices, and having basically solving AX equals B, or just computing A minus 1 is just the inverse of computing. It's the inverse of A, and then you have that the QR decomposition, for example, is the inverse of multiplying an orthogonal matrix times an upper triangular matrix. So these are inverse maps, and there is all I'm writing a paper on how these things are done formally and all that stuff. So you can also compute the derivative of the SVD, and you can compute the derivative of the QR decomposition and the LU decomposition and so on. Only that these things are slightly trickier, but that's why we have PyTorch and JAX and TensorFlow. You don't need to know how to compute these derivatives as long as they are implemented that. But just for you to know that, there's can go beyond this initiative. And I sent to the organizers like some notes on this. I think that they might have already sent them to you. So the complex number stuff is treated in those notes, and basically this covers almost all those notes. But like I would very much recommend you, if you are interested in like really learning these things, which I think that they may be very useful for you at some point, I guess. Like go read through those notes. Those notes will be basically like it gets slightly more slightly more in-depth version of this, but like not much more really. So you should have all the like more than enough with this we'll cover in this presentation to be like go through those notes. And also there is an exercise where in those notes where you need to implement the derivative for a two layer neural network. And like I wrote the boilerplate of the I wrote the boilerplate of the code. So you just need to write the derivative. You first compute it, implement it in PyTorch, and there's a grad check that will tell you like you got it right or not. And that's all I had. Thank you very much.
So let's take a break now. If you have questions for Mario, ask them over the break. We will reconvene at 11:10. So we're very happy and lucky to have Suyan Chung from who's joined between NYU and the Flatiron Institute in CCN give us a talk on some very cool stuff that she's been doing recently, helping us understand analytically what's happening in deep learning.
Great, thanks. So yeah, can I just get a quick show of hand on your background, perhaps? So how many of you come from machine learning? Okay, and then those of you from other sciences, okay, physical sciences, neuroscience. Okay, cool. Okay, so good to know. So my background is in theoretical physics and applied math, but I currently am a theoretical neuroscientist. So I'm going to share with you this in an interesting way of analyzing deep networks and neural data using the methods from theoretical physics and geometry. Yeah, so, oh, just one second. What have I done? Okay, yeah, so a central question in understanding how the brain works is to describe how a collection of neurons or networks of those neurons implement behavior in a collective manner. In order to understand this, we tend to formalize, as neuroscientists and also statistical physicists, we tend to formalize the behavior or computation as functional tasks in perception, and cognition and action. And in order to understand how these tasks are implemented by the brain, what we do is to inspect the neural activity that is experimentally extracted and also discover the plasticity learning rules to understand how these neurons learn. But you can also apply the similar analogy to the deep networks by extracting features and also looking at the learning rules and looking at the collective behavior of those. So the structure of these collections of neurons or units manifest themselves as representations and the collection of these learning rules as network learning dynamics. And what we are interested in is looking at the neural networks as a model to understand neural circuits, because we do have full access to their internal representations, and we can also test the consequences of individual bioplausible learning rules rather easily. But in many ways, these neural networks are still a black box, and understanding and interpreting how they operate requires theoretical and mathematical advances. And in order to do this, we have been using the methods and techniques from theoretical physics, specifically statistical physics, and incorporate the techniques from machine learning to develop a theory of neural networks. And the goal here is to use the theory to develop intuitions and guide experiments, and also explain the observed phenomena in the real data. So there's three related methods that is going to interact in this talk. So one direction that has been actually very helpful is to develop the theory of neural population structures or geometries. And what we did here is to develop a theory of task-efficient neural population geometry to answer how we can interpret high-dimensional neural activity or feature space and connect it to the implementation of a specific task. And second, we're going to use the geometrical insights to understand the structure in these neural networks. And finally, what we have been also recently doing is developing biologically plausible learning rules that can work effectively on a network level. And also, before jumping into the details, if you have any questions, you should feel free to interrupt, because if you're in the audience wondering what the hell I'm talking about, there's some chance that others will be secretively thankful. So, okay, let's jump into the first theme, which is, in my opinion, the most exciting part of the talk. So let's say we're given a stimulus, like a picture of a dog. Then we'll have a population of neurons, but the analog of that in a deep net would be that there will be a bunch of features responding to the stimulus, and that's going to be a point in a high-dimensional state space. This can be a feature space in a deep net, or neural state space in the neural data. This is typically in high-dimensional space. So if you have n features, this will be n-dimensional feature space, and that's now about a single object. But we know that in real life, these objects or stimuli that we have to see, they move around and rotate. And what happens, and then what happens, so if you have these variabilities that we have to overcome in doing a classification task, is that these changes in the stimulus space, they move the firing rates, and then your representation of a dog moves around in this stimulus space, and it forms a manifold of a dog. So this so-called neural manifolds are a direct consequence of structures and how each unit or neuron is responding. So in neuroscience, or in the early visual system, we tend to think that neurons have tuning curve properties, which is a basis for neural coding. And the manifolds or geometric structures from the populations of sharply tuned neurons will look differently from the ones from weakly tuned neurons. And the hypothesis that has been actually quite fruitful is that if we can decipher the structure and the computational role of these neural manifolds, then we can actually start to understand something about how tasks or cognition is implemented in a collective manner. And indeed, there has been a lot of exciting work at the intersection between computational neuroscience and deep learning on the structure of task representations in neural or feature representations, both in biological neural circuits, but also in network models. And these observations are coming from not only the sensory systems like vision, but also starting to emerge in motor control, motor cortex, or higher cognitive areas in the brain, like prefrontal cortex and hippocampus. And we recently wrote a review paper about this trend on thinking about the distributed neural representations with the geometry. In this paper, review paper on current opinion in neurobiology. So if you're interested, there's a good survey. So a lot of us are excited about the prospect of using neural manifolds or the populations of neural representations or geometry of neural representations to understand cognition and the implementations of a task. And the specific approach that we have been taking is the following. So first, can we build good geometrical measures to characterize these task encoding neural representations or manifolds? And then can we connect these geometrical measures with the task efficiency or the performance from the perspective of a readout? To answer these questions, we're going to focus on a specific task to formalize the problem, and let's consider invariant object recognition as a task. So invariant object recognition refers to our ability to distinguish between objects across all kinds of stimulus variabilities, like different sizes or orientations or positions or backgrounds. And it is one of the most commonly solved tasks by the brain. So first, let's go back to the earlier example. So we want to represent this invariant object recognition problem in the neural state space as manifolds. So remember how we went from a single example of a stimulus to a point in the feature or neural state space, and then we went to manifolds due to the variability. And now what happens if we have another object class, like a picture of a cat here, and then that becomes a point, but with variabilities, then it'll become a cat manifold. So now two objects with variabilities, they become two object manifolds, a cat and a dog manifold. And now you can represent the task of discriminating dogs versus cats and also other objects as a problem of separating these object manifolds in the feature space. And in geometric terms, it means that if we can draw a hyperplane between these object manifolds, we are able to separate them. And sometimes I'll refer to this as a linear discrimination. You might have already learned this in earlier classes. And it just means that we want to discriminate these object manifolds with a straight hyperplane. And hopefully you can already start to see what kind of questions we can ask here. So for example, we can ask how crowded can we make these object manifolds in a given neural state space with like 100 or 1,000 features. Okay, yeah, go ahead.
It's like, let's say a cat manifold, is it like a manifold of all the cats or just of this like specific?
Yeah, that's a good question. So I think you'll probably see what this will become clear in the next slide. We're going to relate this to the classification capacity, like VCD mentioned. And the short answer is that it actually does not matter if you have a smoothly varying manifold or if you have a set of points and then forming a point cloud manifold. So yeah, so far, so for the theory, it actually doesn't matter how the manifold is generated. It's going to be the set of points or set of vectors corresponding to the same category label. But often they are generated, often the relevant manifold becomes something like a data augmentation manifold where you start with a single example and then you move things around a little bit. Obviously in real life, nothing will be completely smooth, but I guess we're calling it a manifold, assuming that there is some underlying smooth structure. But in reality, we often deal with discretized versions of these points. Yeah.
Sorry.
Yeah.
Is it like also assuming, are you also assuming a single manifold throughout all of the possible stimuli, or is it like be multiple different like disconnected islands?
Yeah, I think here the more relevant question, more relevant definition is disconnected versions of manifolds. So again, I can imagine like if you have a dog class manifold, then there's a lot of holes between different images of dogs. But for each image of a dog, you can generate like a smooth manifold. So it'll be like islands of different dogs. But if the question that you want to characterize is categorizing all the dogs from all the cats, then there's going to be islands of manifolds. But if the task that you care about is actually differentiate or discriminating between different exemplars, given all kinds of variabilities, then you'll be dealing with the compressed and nicely connected manifolds. So the kind of question that we can ask here is, what is the role of the degrees of freedom, like the dimension, or the size of these manifolds in the geometric space, and how they can be packed up into the complete neural state space that we're given, which has to do with the number of features that you specify in a network. And more broadly, can we quantify and formalize the actual linear separability of these object manifolds and relate it to their underlying geometry? So as it turns out, there is already a very well-developed theory of linear classification called the theory of perceptrons. And this was developed separately, both from theoretical physics and also from computer science. And some of you might have heard about terms like BC dimension or Cover's theorem, but it's okay if you haven't. The idea there is that if you have p points, and if you're assigning, and then there's, and if let's say you're assigning a plus and minus labels randomly to all of your points, and then there is going to be 2 to the p scenarios of assigning these labels. It's called dichotomy. So each scenario is called a dichotomy. So given all of your dichotomies of p points that are embedded in n dimension, when do you start to have when do you start to go from mostly being able to separate them to mostly being able to being able to not separate them? So that's the transition of going from being able to find hyperplane, linearly separating hyperplane most of the time, almost 100%, to transitioning to 0% separability. That's defined as linear separability. And the capacity of a problem from the perspective of a perceptron, which is the linear hyperplane. So so this is a very well-established problem in statistical learning theory. And here, the capacity of a perceptron refers to the maximum number of points per feature that can be linearly classified. So if your capacity is 1, that means that given 100 dimensions, you can classify 100 points. If your capacity is 0.5, that means if you have 1,000 dimension, you can classify 500 points. So that's the notion of capacity. Now, but unfortunately, this idea of perceptron capacity is about discrete points, which is just a single realization or instance of a memory. In other words, I can recognize you at this second, but if you're moving just a little bit away, you have just generated infinitely many points along that small trajectory of moving. And this theory will not be able to tell you if I can still recognize you. So in real life, what we have to do is to overcome these kind of changes in the stimulus space. This is a problem that we need to actually resolve all the time. And what we actually need is the perceptron capacity of classifying manifolds for real life problems of invariant object recognition. Because as I said, these object manifolds with all the realistic variabilities can have infinitely many points. So the predictions on how many points you can linearly classify is actually somewhat irrelevant. So this is exactly what we developed with Heimson-Polinsky and Daniel Lee, which is the theory of classification of object manifolds, which now tells you the maximum number of object manifolds or category manifolds that you can linearly classify per unit. So remember how we defined the capacity with this random dichotomies of labels, and now this is very similar, except for that now the counting units for capacity is going to be categories rather than individual points. And for those who might be slightly more mathematically inclined, this is sort of how we derive it. So to compute the capacity of the manifold classification, we need to compute the volume of the solution in the state of the solution weights, where if you have only few manifolds, then it's an easy problem. So there's a lot of solutions. So the volume of the solution for that qualify as a linear separator is large. But as you start to put in more and more manifolds into your state space, then it becomes harder problem, and the volume of the solutions decreases. And at the critical capacity of classifying manifolds, then this volume of valid weight vectors, the solutions, it becomes 0. And how do we compute the volume of the solutions? So that can be done by integrating over each dimension. So if you have an n-dimensional feature space with a linear perceptron, then it's an n-dimensional problem. So you have an n-dimensional integral over each element of the perceptron. And you can constrain the size or norm of the hyperplane solution. And you do a product of the step functions, where the input for the step function is the difference between the distance between the worst point to the hyperplane minus the required margin of the problem. So what this is doing is, if you got all of your manifolds on the correct side of the hyperplane, then all of these inputs will be positive, and the step functions will give you 1. So, and then you'll do a product of that. So it will contribute. If you get everything right, it'll contribute to the volume of a solution. But if you have one manifold that's been classified a little bit wrong, then this term will be many ones, but multiplied with 0. So as soon as you have something wrong in terms of classification perspective, then the contribution from this term is going to be 0. So this is how you capture the volume of solutions given the representation with certain geometry. Yeah, go ahead.
How is the boundary of a manifold defined?
How is it defined?
Yes.
Yeah. So this is an emerging line of papers, which is it's a really good question. So there is did I put the citation here? So in the physical review E, we define the manifolds as spheres, so it's very well defined. And in the physical review X paper, we define, we compute the capacity of general shapes with arbitrary points. Then we're dealing with convex halls of point clouds. Now, I think the next set of papers that will come is probably going to take into account having some of the points classified wrong. You allow for some slack variable, and you probably also have a version with probabilistic distributions and so on. But yeah, so far, it's the boundary of the manifold is defined as the worst point from the perspective of the hyperplane. And if you have a spherical manifold, you can analytically calculate it. If you are talking about classifying the convex hull of the point clouds, then you do an iteration on which point is the worst one, and then you look at the statistics of the distributions of the worst points from the perspective of all kinds of different dichotomies of the hyperplanes. Yeah.
Okay.
Yeah. Yeah. So and computing the volume of the solution over this high-dimensional weight space is a little bit complex. So what we do is to invoke this trick called replica theory from statistical physics, which allows you to calculate the volume in a high-dimensional space with some approximations. What I think is so exciting and powerful about this kind of theory is that it's both multi-level and analytic. So I'll talk about what that means as we go on. So I just sort of gave you the proof sketch of how we can compute the capacity. but can I just maybe, oh yeah, but okay, so maybe I'll go through the equation first and then get your question. It's worth talking about what capacity here really means, because it can be interpreted as multiple ways. So first, it's about how easy or hard it is to discriminate the real life objects away from each other in their particular representation, like ELF layer of a deep net. But it's also about how many categories can you remember or linearly classify given the representation that's been assigned to me. So it's also related to memory capacity in the given representation. And it's also about per unit or per neuron information content about object classes. So it's also about how efficient the given units or neurons are in representing object classes in a representation that's been given to us. And what we did just now is to use a StatMech approach from theoretical physics called replica theory, which allows us to calculate this manifold classification capacity explicitly. And I won't go into the equation term by term, but we can look at the simplified form of this equation. And we see that the manifold capacity can be expressed in terms of each object manifold's geometrical properties, such as the effective radius and effective dimension of object manifolds. Yeah, and then before I go into the summary of this theory, maybe I'll take the question. Yeah.
So maybe you said this, but I didn't understand. So when I have a set of points, the dichotomies are easy for me to understand.
Right.
Well defined, like no
Right.
classes for the classes.
Yeah.
I'm not really sure how, if I have a set of points, how I do dichotomies of manifold.
Right. Yeah. That's a very important question. So what we do is the assumption here is that all the points within the same manifold or category will have the same label. So you're doing the assignment of labels at the category level. So that's, yeah. So yeah, does that make sense?
Okay, maybe I misunderstood them that dichotomies at the beginning. I thought you have like, theoretically, you have a set of points which can grow, and you don't know the categories beforehand, and you are setting the categories randomly. Yeah,
for this manifold, you need the tags for categories. It doesn't have to be the ground truth tags for categories, but whatever you want to evaluate. So given, let's say you have like a CFAR 100 data set, which has super categories and leaf node categories, you can define the manifold at the leaf node level or super category level, and it'll pop out capacity and geometry. Yeah. Yeah, so let's talk about, okay, so what does that mean? Like, I want to understand exactly what it does. So the key results of the object manifold classification capacity theory is that there's 4 properties that matter so far, although it can be honed even further, but this is what we have so far. The manifold capacity is a task level measure, which tells you how separable these categories are, and how many categories you can invariantly discriminate. But this will be affected by the geometrical properties of neural activities, which is characterized with effective dimension of the manifold and effective radius of the manifold. Now, dimensionality is a big topic in both deep learning and neuroscience, and there's a lot of different definitions. But here, this is the dimensionality of each category manifold or data cloud relevant for the linear classification capacity. And the same for radius. There's a lot of different ways to measure the size of the data in high dimensional space, but this is a measure of the size of the data manifold relevant for linear separability, and it's affected by the elevator pitch version of the, what it is affected by is something like support vectors from different shattering hyperplanes. And so depending on how you define the labels, the worst points will be different, and the statistics of those worst points will determine the dimensionality and radius of the manifold. It also turns out that in real data, you also need to take into account the correlations. So you can think of the correlation as the similarity between different classes So for example, in a cat versus a lion, they are more correlated than in a cat class versus a car class. And as a first order approximation, including the correlations between the centroids of these object manifolds make the theoretical method work. And how are they related, and what does that actually tell us? It's easy to understand what this is doing by thinking about two scenarios. So we can consider the high dimensional representations where the object manifolds are highly tangled, like early layers of a deep net or before learning some kind of task, versus nicely untangled representations, which you might see in the later layers of a deep net or some deep area of the brain. If you have the manifolds that are highly tangled, then the theory will say that the capacity will be low, and that's usually driven by the high dimensionality and large sizes of these manifolds, or high correlations between these different manifolds. And the intuition here is that it's simply too hard to pack large and high dimensional and extremely correlated object manifolds into the neural state space such that they're linearly separable. So it's a little bit like packing of spheres into a box kind of problem in physics, except now we're talking about packing object manifolds into the neural state space, and you're allowed to have some overlapping of the manifolds, unlike the real sphere packing problem. And you might see this kind of representations in early regions of sensory processing, like V1 or the first few layers of a deep net, or before learning. And you'll see some of the examples in the next section. On the other hand, if you have object manifolds that are really nicely separated, that are ready to be applied a softmax layer of, then you will be able to classify many of the categories. So the manifold capacity will be high. And in order to have the high capacity of high classification capacity of manifolds, then that's usually driven by the small dimension and small size and uncorrelated locations of these manifolds, different class manifolds. And again, this going back to the sphere packing problem, it's as if you have a box like a state space, it's a lot easier to pack a lot of small disks or coins than large balls. So you'll be able to classify many more of object manifolds if they're low dimensional and small in their size. And the progress of this theory is that you can actually explicitly predict what the classification capacity is going to be based on the geometry of these object manifolds. And I should also note that these geometrical properties, they don't always move together. So in a real data, you can have a tiny high dimensional noise like neural manifolds. It could be something like adversarial perturbations. Those would be tiny but high dimensional. But you could also have low dimensional but flat and long manifolds, like a trajectory of something. And what's fun about this theory is that it'll capture how these different geometric properties like dimension and size or radius, it'll combine together to determine the capacity. So it can also capture the trade-off between the dimensionality and the size of the manifold. So just to give you a full flow of how this can be used, the theory of classifying feature or neural object manifolds can be used as a multi-level probe for looking at neural representations. So given the representations with category tags, which don't have to be smooth, by the way, meaning you can, again, have point cloud data, this method will compute the geometrical properties and predict the manifold capacity using the physics analytics. And this has a lot of interesting implications for neuroscience and deep learning. So first of all, these neural manifolds or object manifolds, it can provide a mechanistic underpinning for how tasks are being implemented, and it can be used as an interpretability tool. Because you can now look at the structure in the high dimensional population space without assuming that they are low dimensional. So you don't have to do like a dimensionality reduction to be able to understand how the data is structured, because now we just go in and take the full dimension and then evaluate their geometry using this method. And the neural manifold geometry is a consequence of collective properties of neurons or units. So, you know, like training curve structure or receptive field and their distributions, or the nonlinearities, the nature of nonlinearities used in nonlinear units like ReLU versus sigmoid versus tanh. So by connecting the representation geometry with the probe or readout performance, we're one step closer to understand the role of individual units or neurons in implementing a task, because it's a lot easier to connect the unit level properties with representation geometry than going from the units to the task level measure directly, because that's two levels high up in abstraction. But now that we have a formal connection between task level performance with representation geometry, we can now we just need to connect the unit level properties with the representation geometry level. So I'll talk about how this can work by demonstrating this in deep networks in the next section. So this section is about understanding the population structure with geometry in neural networks. And just as a motivating slide, there's a lot of recent reports showing the representational correspondence between artificial neural networks and biological neural circuits. For example, the work by Daniel Means and Jim DiCarlo at MIT have shown that task-trained deep networks can predict the neural activity pretty well in monkey ventral stream, macaque ventral stream, and it's also been shown that the neural population structure and the geometry are quite similar using the similarity-based measures. Now, then you can ask if these neural networks are so good at predicting the brain data and quite similar in their structure, then why don't we just study artificial neural networks as a surrogate system for neural circuits? That's totally fine. But one challenge still is that while these deep nets might be similar to the brain, understanding and interpreting how and why task representations emerge is still extremely difficult, but we should still take full advantage of the opportunity of knowing and having full access to everything in the network, unlike what we can do in the brain. So yeah, so to do this, what we are doing is to use neural manifolds or geometry framework as an intermediate level descriptor to connect the representations and task performance in each layer, to understand neural networks, again, as a model system to understand the natural intelligence, and also as a test bed for new analysis tools. Yeah, go ahead.
Could you speak a bit more to how closely related like a neural state space is to what's actually happening in the brain?
Yeah, so in the brain, you have a spike counts. So you have a temporal response with the number of like how many spikes are happening, and then what we do in neuroscience is to take the bin, like some time window period, and then you count it, and over many trials you can average it, and then you get what is called a mean firing rate, and that's essentially from the mathematical point of view, if you have 100 neurons with firing rates, that can be, it's mathematically equivalent to the features, 100 features in the deep network.
So that would correspond to like a 100-dimensional space?
Yeah, okay. Right. So in reality, in real brain, there's a lot of stochasticity. So we have much noisier data, while in deep nets, unless we explicitly include stochasticity, you'll have deterministic representation. But as far as the comparison between deep nets and the brain data is concerned, that's the standard for the matrices that you use to compare, which is firing rates, like a matrix with number of units versus number of stimuli, and then the same in a deep net. So yeah, so to do this, we have been applying several different geometrical techniques to study different problems, going from vision to addition to language in neural network models that are known to predict neural data. And also, we've looked at the experimental data like Macaw ventral stream with in the collaboration with Jim DeCarlo Lab, and this is the list of experimental collaborators growing now. And today, what I'll highlight is the two recent studies in vision and audition. So let me start with the work on understanding pre-trained visual deep networks. And the goal here is to use manifolds or representation geometry to understand how deep networks process information layer by layer as a testbed for neural circuits. Now, AlexNet is one of the standard deep networks to study vision, and they're also shown to predict primate visual cortex neural data pretty well. So let's use that and use ImageNet data, again, a very common benchmark data set for vision. So with ImageNet, we can simply define object manifolds as pictures in the same object class. So different exemplars of dog photos will form a dog manifold, although it's more like a point cloud, and so on. But you can make also the smooth and then well-connected manifold by taking a single image and moving the image around by applying a bunch of different transformations, like changing an angle smoothly or making it slowly bigger or stretching it and so on. So those will be stimulus variation manifolds, which are more related to something like a data augmentation. Now we can run these kind of images on AlexNet and extract features like you would in neural data, and we can recover object manifolds from the AlexNet from each layer. And then we're ready to apply the neural manifolds method and theory. So what we're going to do is to ask how discrimination information or the classification information improves across layers of a deep network. Now, before showing you that, I just wanted to show you the sanity check slide. As we were advertising in the first theme, the theory of manifold classification coming from the geometrical measures can be compared with an empirical manifold capacity, because this classification capacity based on dichotomies, it can be evaluated even without knowing any theory, because you can take let's say like 50 example classes with 50 samples, and you will have and then you extract those the responses from the deep net, but you can reduce the number of features by just projecting it to a lower and lower dimension. And you will start to see that the dichotomies that you are looking at were mostly separable in high dimensional space. But as you're going into the lower and lower dimension, at some point it'll start to be inseparable. So you can actually get the manifold capacity empirically, and we can check that the replica theory predicts the empirical manifold capacity, which means that the geometrical measure that we're going to be looking at it's analytically related to the real classification capacity. So now with that, we can follow the manifold capacity with the three geometrical measures that we just talked about in each layer. And this is what we see. It's actually moving almost as predicted. The manifold capacity is increasing, and which means that the efficiency for the units in a deep net in representing the classification information is improving across layers. But I mean, you could do this with the softmax layer trained on top of each layer as well. But what we can do with this method is we actually know that the improvement in the capacity is because of the reduction in the manifold dimensionality and reduction in the manifold size and the correlations between the locations of these manifolds. So this is the benefit of having a causally linked multi-level probe, because we know that when there's an improvement in the information packing, we know that it's because of these kind of changes in the dimensionality or the geometrical properties. So with the full access of the information content and the geometric summaries at each layer, we wondered, can we then now understand what each layer of this network does? And can you check these properties before and after a certain network component or specific layer? So that's what we did. You can take the ReLU layer and then extract features from the before and after ReLU layer and look at the geometries. So I'm showing the change in the dimensionalities of the manifolds and the changes in the correlations of these manifolds. And remember, for increasing the capacity, we want to decrease both the dimension and the correlation. So you want to be in this green part, like negative quadrant. But what we actually see is that ReLU tends to be occupying this area, which means that ReLU is good at decreasing the correlations between different manifolds, but it actually ends up increasing the manifold dimensionality. So ReLU does something good for decorrelating, but it comes at the cost of increasing object manifold dimension. And you can do this for other types of layers like pooling or combinations of different layers, and also look at different geometric measures. And I'll just summarize that in a table. So this is what I just showed you. The dimension goes up and the correlation goes down with the ReLU layer. And then the same thing with the radius, which shows that the activation nonlinearity layer reduces the two properties, but it comes at the cost of increasing the dimension of the object manifolds. You can also do this for other nonlinearities like max pooling units, and it reduces both dimension and radius of the object manifolds, which is good, but it ends up increasing the correlations between different classes. So it turns out with just a single layer of a same units, there's a trade-off between the geometrical properties. But if you look at the common circuit motifs, like convolution followed by ReLU, followed by pooling, then what you end up finding is that the dimension, radius, and correlations, all of them can reduce favorably together. So this is, in my view, a really fun and powerful application of the geometrical way of thinking about what each layer does in deep networks. So just to summarize this project, what we're seeing here is that the geometrical way of thinking uncovers the mechanism underlying favorable circuit motifs and their combinations, and the limitations of a single layer of homogeneous units. More generally, this also shows the power of geometrical framework as an intermediate level descriptor between task implementation or efficiency and the representational structure. So, and I know this is a very biased view, but I think there's so many things we can do starting from here. So after identifying the geometrical role of each circuit motifs, then we started thinking, well, we can probably impose some additional neuron-like constraints on the network and understand the role of those bioplausible constraints on the deep net from the neuroscience perspective, but also from the neuro AI perspective on like what kind of neural units improve the circuit performance. Oh, you have a question?
Can you go back to the last slide?
Yeah.
Actually, one before this. So, pretty mentioned correlation. What ensures that it's not like a zero-sum game? Like, are the successive layers like the magnitudes of these changes?
Right.
Yeah.
Oh, what ensures that it is not like a zero-sum game?
Yeah, like the dimension might increase in one layer and the next layer might decrease.
Right.
Phase two different things. Like, does the magnitude of those changes getting smaller so that like
oh yeah, why doesn't it like oscillate?
Yeah.
Or do we know that it's not oscillating?
Yeah.
So I mean, I think that's just shown by the summary picture here. Because if you look at what's happening across all layers from the input all the way down to the output, then overall the dimensionalities go down and the radius also goes down. And what we were just looking at was so I think I got rid of ReLU here for the sake of like not crowding it too much, but after the max pooling, we have a ReLU. So we were sort of dissecting here and then looking at the comparison between the two. So I mean, so this is telling us that globally there's a trend of reducing the dimensionality and making the manifolds smaller and then making them uncorrelated. But if you look at specifically what all of the ReLU units are doing, they are here. But I guess there's an oscillation. There's a trade-off, but I guess by doing it in a successive way and also in a way where you combine different nonlinearities like next to each other, somehow you are able to push them down in all negative directions. So I guess, well, there's more work to do for sure, but I think what we're seeing is that having different types of nonlinearities or different operations together, it gives you a better expressivity, or it gives you more expressive power of transforming the object manifolds in a way that's favorable in linear separability. But yeah, I think being able to say why it is not a zero-sum game in a formal manner will be extremely interesting. There's got to be some things that you can do by looking at the properties of the weight structure and which neurons or units end up being zeroed out and all this stuff. And that's for interesting future project. Yeah. Go ahead.
Do you have some experiments when you start training, like in the first tables? How is the capacity?
Oh, like how does it change across learning? Yeah, we have a paper about that on, let me just point you to this, let's see, slide before. Here, this iClear paper, it's called the Geometry of Generalization and Memorization. We look at the learning dynamics. So as you're training the network, how the geometry and capacity changes. And you can see that the capacity is clipped at the lower bound across all the layers before training because the weights are random. So it's as if you know, and there's probably some structure in the input space, but from the classification perspective, they are very inefficient. So it's usually clipped at the lower bound. And unlike what we see in the pre-trained network where the capacity improves across layers, at the initial condition stage, they're flat. But after one epoch, you can see that it improves. Actually, a lot of the structural work with geometry is done mostly in the first epoch, which is extremely interesting. Yeah, so you can look at, you can slice it in any way you want. You can look at the learning dynamics with the geometry. You can also look at the layer-wise. You can also look at the batch level. Yeah, you can change the ordering of images and train it and see how that affects the geometry. There's a lot of things you can do. Yeah, but yeah, this paper has the geometry of learning dynamics. The speech paper also has something like that. Yeah.
Just, I think your mouse pointer is off between your laptop screen and the big screen.
Oh, sorry?
Your mouse pointer,
Yeah.
I think, is off between your laptop screen and what you're sharing. Could that be?
Oh, isn't it here?
Yes, but is it also there on your screen?
Right.
Is that correct?
Yeah.
Okay, okay.
Oh, it's actually a little bit offset. Yeah, sorry about that. Thanks for putting
I'm not like, maybe I'm just wrong, but
yeah, so this is the Geometry of Learning Dynamics paper. I was probably pointing at something else. And the speech paper also, I guess these three papers, this is specifically about looking at the learning, but both of these papers actually, we show the capacity improvement and geometry reduction, like dimension reduction, but there's also like a baseline line of like random weights at the initial condition. So you can see that they are different. Let me see. Oh, I didn't realize the cursor was off. Yeah. Yeah, and this is also a little bit, so yeah, I guess we're dividing this by lower bound, but if you don't train the network, it's clipped mostly at the lower bound. Okay, so let me just walk you through the other section, which is also somewhat exciting. So what we did in this project is to introduce something that's neuron-like. And as I said earlier, real neurons are stochastic. What we did in this project with DiCarlo and McDermott lab at MIT is to study the connection between the role of neural stochasticity in a phenomenon called adversarial robustness. And let me just explain what that is. So let's say we have an image of panda like this one, and it's easy for both humans and networks to recognize this as panda. But if you add a tiny little perturbation bounded by some epsilon size at every element of a pixel, and then you feed it through the network, then while this still looks like a panda, this image still looks like a panda to us, but the network is very confident that it is a given. And this is an interesting test bed because it's a case where we see the divergence between a deep network and humans, where the humans are performing much better than artificial networks. And it turns out that if you make the network more like the visual cortex or real brain by adding a front end based on classical linear and nonlinear Poisson model, as in you inject a stochastic noise after the first layer of filters, then all of a sudden it makes the network more robust to adversarial perturbations like the one that I just talked about. And this was the result shown by Jim DiCarlo and coworkers. So while there was a phenomenon, it wasn't quite clear how and why it happens. And there was also some conflicting reports on the role of noise about whether it is helpful or not for the adversarial robustness. So what's going on here? So this is where it'd be great if we can go in and geometrically understand how adversarial perturbations are affected by neuronal constraints, like stochastic noise. And we can, in fact, define the adversarial perturbation as an epsilon size, the small manifold. And we can also define the stochastic noise as a clouds of noise around the response to an image. So we looked at two different types of manifolds, and we identified two interesting geometrical effects that compete with each other. So first is the positive effect, which is that if you add a stochastic noise, then the noise cloud around a clean exemplar image and the noise cloud around an adversarial perturbation, they start to overlap with more noise. That's kind of obvious because if they are actually very similar distributions, except for the small offset due to the adversarial perturbation. But it's interesting because if you don't have such noise, these small perturbations, they start to diverge in a classical network. But yeah, so if you add a noise, they end up being a very similar distribution, and that drives the adversarial robustness because it's as if having a very similar training and a test distribution. Now, clearly, having too much noise must be bad for class separability. So there's a negative effect of having too much noise, which you can see geometrically with manifold theory. And I think you can see where I'm going with this. These competing effects of geometry results in a non-monotonic relationship, in a peak in adversarial performance versus the level of noise. And the optimal level of noise should be predictable from quantifying these two geometrical effects. And indeed, we find a high correlation between predicted and observed optimal level of noise. Now, these two effects might seem intuitive, but finding a quantitative balance between two geometrical forces is hard to do without having a precise geometrical measure, which has a connection to the task implementation. So that was quite exciting for us to see. I'm also, yeah, okay. And another interesting thing to think about here is that all of this story about the manifolds, it's quite general. It's not really limited to like a specific modality. So we should be able to see this phenomenon in other problem space as well. Now, audition and speech is the modality where we were able to show the similar geometric phenomena to visual systems in the past, like untangling. So that's a good place to look. So, and we worked with Josh McDermott group who studies computational audition to inject a similar kind of stochastic neural noise into an auditory deep network. And that we found that it also rendered an adversarial robustness without explicit and expensive adversarial training. And the underlying geometry of the noise and adversarial perturbation was also quite similar to what we saw in vision. So let me just summarize the results that we saw in part 2. So first, we showed a layer by layer understanding of how networks process information through geometry to support their tasks. And second, we saw that the geometry helps us understand the role of neural noise on human-like traits, such as adversarial robustness. And in both of these problems, I want to highlight two things. So first, there was a competing effect between different geometrical properties. And this is hard to probe unless we have good geometrical measures. We can always visualize a problem, but that tends to depend a lot on what kind of axis and then a lot of choices on the parameters. And it's fun, but to check exactly what is the role of each layer or the role of each parameter, what you need is a good quantifiable measure of the underlying neural manifolds coming from the full feature space. Relevant for the task, and this is the focus of our theoretical work. And second, these geometrical interpretations are general across the modalities, as you can see from going from vision to audition, and it helps discover the common and unifying phenomena across different regions of the brain or different parts of the network and across different scales. So this is why I think that the neural manifolds or population geometry framework is a powerful and exciting framework to connect different scales and different levels. And I think it'll eventually help us get closer to understand the neuronal distributed neuronal basis of behavior and cognition and tasks. So there's a lot of exciting implications for future work, but for the sake of time, I'll save it for the Q&A later. And I just wanted to briefly show you the other extension or the other direction that we've been pursuing, which is the bioplausible learning. So deep networks have been excellent models of the brain recently. But backpropagation, which is the most commonly used training algorithm, is simply not biologically plausible. And this is because the implementation of a backprop requires the weights in an intermediate layer to have the knowledge of the connections from that middle layer all the way down to the output layer, regardless of how many layers are in between them, because you need to use a chain rule to compute the gradient at an early layer. And that's it's really hard to have that in the brain. Now, there are other traditional plasticity rules such as Hebbian learning, which is more biologically plausible, but their performance is quite bad at a lot of common cognitive tasks. So there has been a lot of recent effort at the intersection between deep learning and computational neuroscience community, trying to understand the nature of biologically plausible learning rules that are also highly performant. So we're trying to push the learning rules into this corner where it is plausible and local, but the performance is quite good at the network level. So that's one of my recent and ongoing work. And to do this, what we're doing is incorporating the new experimental findings from synaptic plasticity in the real brain into the designing of a deep network architecture and learning rules. So it turns out in recent studies in electric fish, it's been shown that continual learning in which case a constant prediction of an incoming stimuli, because these electric fishes, they can send signals to detect where they are in a deep sea, and it needs to actually make a prediction on the incoming stimuli in a temporal sense. And so when you're doing a constant prediction, it turns out that in the regions of the brain that is implementing this kind of computation, and then in this region, there are two types of different spikes that are used for neural computation, the broad and a narrow spike. And what they find is that these two different types of spikes are used for different purposes. So the broad spike is used for learning, while the narrow spike is transmitted downstream to the next area of the brain. So this got us to think, what if we have one signal type that is doing a local prediction with the probability, and another signal type, which is an activity like a real number, that is sent to the postsynaptic neuron, meaning the next unit in the layer. And then they are related with some sort of nonlinearity. And with these two representations for prediction and sending the signal downstream in one unit as an architectural principle, we designed the new learning rule where the update to the weight or the synapse is determined by the product of a pre-synaptic activity like R before the weight, and a postsynaptic local error, which is an error coming from the next unit. And with the principles that we just talked about, we designed a network that's capable of local learning without having to have access to the chain rule or all the layers, the weights for all the layers between the intermediate layer and a final output layer. So yeah, this learning rule somehow works really well, meaning that each unit has its own prediction and it learns with its own learning rule and it performs quite well. And you can have theoretical guarantees like convexity, meaning that each unit learns optimally given its input, whatever is locally available to them. And interestingly, along the way, we also found another hybrid class of local learning rule where this local error is swapped with an output error of a network, which can be thought of as a broadcasting of an error. And it turns out if you add some additional neural constraints, like making the synapses to be non-negative, which is, by the way, like, you know, in the brain, a lot of the synapses cannot change signs. This kind of learning rule, it turns out you can actually prove that each element of an update with this global error local learning rule is matched in sign with the backpropagation without requiring, again, the knowledge of all the intermediate layers weights. So this is now published in NeurIPS last year, as you can take a look. And this theory also makes some interesting experimental predictions with the implications on the representation geometry. So that is, the local learning rule will result in more robust intermediate layer from the perspective of the readout performance compared to the backpropagation. So what this means is that so backprop has a really good performance in the final layer, but the intermediate layers are quite bad. So if you lose the last layer's neuron, then the network will perform pretty bad. But in the local learning rules, even if you lose the last neuron or unit, the intermediate layers will actually have a pretty decent performance, which is related to the robustness in the computation in the brain. So yeah, so it's quite exciting, and there's a lot of work that we can do in coming up with the bioplausible learning rules that can scale well, inspired by the experimental findings in systems neuroscience, and also relating that to the representation geometry of the deep net. So here's the list of the papers that that we talked about. And I think for the interest of time, I think I'll jump to the last slide. So thanks for your attention. And if you have any questions, let me know. Thanks. At Flatiron and NYU. So if you're like a graduating grad student, let me know. Yeah.
Could you say again how you get this local error? Like, how do you get the label for it?
Oh, how do you get a label for the
Yeah.
local error? Yeah, that's a very, yeah, I think you're actually asking the very related question that I have skipped for the interest of simplicity. So if you have a binary task, then it's easy. So you can have, so let's say like you have the activity like some real number, and you do something like sigmoid, and then you get a value that's between 0 and 1. So that's the probability for the prediction that you're making about like one of the classes that you're trying to discriminate. Now it becomes a little bit harder when you have multi-class problem that that you have to decide between 5 different classes or something like that. And what we did here to implement this is to actually vectorize the units. So if you're doing like a 5-class prediction, each unit actually has 5 elements, and they are sharing the weights. So it's a little bit like a convolution, except not in the similar space, but the 5 of the units and 5 of the neurons in the same unit, they have the same synaptic connection to the rest of the next layer. And long story short, you need a vectorized unit, like a 5-dimensional R, and then you do a softmax on that, and then you end up getting 5-dimensional P probabilities, and that's just like what you would have in the output layer. So with that, you can compute the error. So does that make sense?
I'm not sure about, like, if you're somewhere in like a mid layer of
Right.
the network,
Right.
how do you calculate the error then? Like, what is the target?
Yeah, so the paper, the title for the paper for NeurIPS is actually called vectorized neural networks. So if your target is, if your task is to try classifying like 10 digits in MNIST, then if you're showing the image 2, then what you really want to get at is like 0 on the first element, and then 1 on the second element, and then zeros everywhere else. Now in the intermediate layers of the units, we'll have 10 dimension, and they will have some distributed number. So that you're trying to do a prediction on the same task as what you were doing in the last layer. Yeah, it's a little bit funny, right? In the early layers, it's hard to imagine that the early layer is doing something like that. So I think what you can do is to come up with the ways of changing the dimensionality so that early layers are doing something that's more broad, like prediction, or like smaller number of classes. It's learning something that's more broader. So that's a very good like immediate things that can be done to improve it. So the new thing about this paper was the fact that you can have a provable match to the backprop. That's something that's quite hard, not easy to do in a bioplausible learning space. Like a lot of times people come up with a very interesting local learning rules, and they can show that it performs well. But coming up with a provable guarantee on this local learning rule, actually it aligns positively with backprop. That's something that's quite rare. So we showed it with the simplest setup, but I think the kind of question that you're asking is like, what we should be working on now for these papers. So yeah. Okay, so maybe we can go from here. So
okay, I was wondering if the manifolds you were studying were all like Euclidean manifolds, and if it would be helpful to like study maybe non-Euclidean manifolds and like maybe I don't know, study more properties of the manifolds, like the coordinates or something?
Yeah, absolutely. So I think one of the projects that I have is to try. Yeah, I agree with you. All of this was done in a Euclidean setting. But I think if you can define the distances in some sort of like hyperbolic geometry to take into account the fact that there's some curved representation, that would be very cool. Yeah, I agree.
I just got curious about this difference between broad spikes and narrow spikes. Is it from like the signal, or what does it mean? Like
there are different parts of the neuron. So it's not the
Is it like the temporal scale?
Oh, it's not temporal scales. I mean, the broadness and is temporal because if we're looking at this like the shape of a spike, but where you find is different. Like they're located in different parts of the yeah.
We make connections to work about like when neural networks can learn disconnected decision regions or connected decision regions.
What do you mean by connected decision regions?
So like if you have your input data, and if you like, let's say like color code each data point by which class it's supposed to belong to, a connected decision region for a class would be where like they're not two separate like blobs of color, I guess. It's like every data point in the class is like connected in like a in like a set, I guess.
Oh, so instead of having like discrete labels, can you actually turn it into something continuous?
Well, not necessarily. Just like if you had like I guess like a 2D distribution, and let's say your decision region was like concentric circles. Like one circle is one decision region, and the outer circle is like a third decision region. Like, and then maybe like an external decision region, which is like the same as the middle one. So it's like a very kind of like hard problem to learn, I guess, if your neural network only learns connected decision regions because it can't learn like at the middle one and the outside one.
Oh yeah, right.
Yeah.
So what? Yeah, but what's
it's like have you made like connections to that and like that kind of work and like that? It seems like they could be related.
Yeah, I think in thinking about how these manifolds are being transformed every layers, and it continues to get processed so that in the last layer they become separated. It's hard not to think about exactly what each unit is doing, and in the stimuli space, presumably some unit downstream or in the first layer is like if they have their own receptive fields or the region that they are responding to, and how those are shaping the manifold geometry in a local manner and also the global manner. It's an extremely interesting question, and I think we can make progress by focusing on the fact that the deep networks are piecewise linear. We're working on it, and it's a very interesting question. Yeah. Any other question?
So let's see on the end. Now
so as I was just saying, as a recap, during the last lecture, the task that we wanted to do is essentially to solve is to find approximate ground states of quantum systems. And again, we set up all the notation for those of you who are not familiar with quantum mechanics. But at the end, I hope I convince you that this is all about considering some Hamiltonian matrix H, which, as I was mentioning, is a in general a complex valued 2 to the n. So this is a complex valued Hermitian matrix of sites, if you want, 2 to the n times 2 to the n for the case of spins that we studied, spin 1/2 that we studied last time. And then the goal there was really to find what I called, I think, psi naught, psi 0, and its energy, so it's zero. Where I told you that these are just eigenvalues, and so E0 is the eigenvalue, and psi 0 is the eigenvector of this huge, if you want, matrix. Okay, and we used this Dirac notation that I also briefly explained to you the last time. Okay, now the main complication was that this psi naught is a sum of, in general, I mean, if we want to try an approximation for this psi, let me call this now psi without naught, in terms of some basis states that I called k. So in general, the problem is that when k goes from 1 to the n, in this case, the general was that problem was that the number of coefficients that you have to store in memory if you want to have an exact approximation, exact expansion, if you want of psi, is exponential. So we don't want to do that. And instead, we would like to approximate, if you want, this ck with some, if you want, function that specifically we took to be a neural network that takes as an input this integer k, if you want, or this string of plus or minus 1, and depends parametrically on some parameters theta that could be the weights, the biases, or whatever you have in your neural network. Okay. And then what I told you was that what we would like to do is to minimize what mathematicians call the Rayleigh quotient, and what physicists call the expected value of the energy, which is just this quantity here. So it's this, so psi, notice that now psi, because of this thing, will depend parametrically on theta as well, because the coefficients, if you want, of this expansion depend on theta through this dependence. So we want to expand, if you want to minimize this expected value of the Hamiltonian. Okay. In general, this wave function is not normalized, so we have to also divide by the normalization. Great. So this was in a nutshell what we saw last week, last Tuesday. And we started looking into the problem of how do we actually estimate this quantity, right? Because if we think that its size an exponentially large vector, we are, back to square one, because just to compute this matrix vector product and the linear product with itself, we will need to do exponentially large summations. But I will not go again into the details, but we saw towards the end of the last lecture that we can estimate. So estimate this expected value of the energy, so this E of theta. Of the quantum energy, if you want, right? Using a very nice idea that is as old as the 1960s, was found by Bill McMillan, was one of the pioneers of what we call variational Monte Carlo. And the idea is that if I want to compute this expected value of the Hamiltonian, right, by doing some manipulations that we saw in detail last week, so I'm not going to do it, I can write this as the sum over k of some probability distribution P of k of an estimator that we call the local energy in the case of the Hamiltonian. Okay, and we derived this formula in detail last Tuesday, but P of k is essentially proportional to psi of k squared, which in the previous notation is just, if you want, this coefficient ck squared. Okay? These are all identical notation, equivalent notations, so I call these coefficients ck in here. Sometimes I call them ck, sometimes I call psi k, but I hope that it's clear from the context that they are the same object. So this probability then is proportional to the square of the amplitudes of the wave function, and then this estimator E log of k. The definition was this is going to be the sum over k prime of all the matrix elements of the Hamiltonian h k prime, and then I have this ratio psi of k prime psi of k. Okay, where again, psi, these coefficients now are given by a neural network, so I can query the neural network to give me a value of psi k for an arbitrary k. And the key point, the crucial point that we discussed also in detail last Tuesday, sorry, is that these matrix elements are sparse in the sense that if I fix k here, the number of k primes I have to sum upon is only polynomially large, so I don't have to sum all the 2 to the n k primes as in the original summation for the most general h. But physical Hamiltonians have this property that the non-zero elements are only polynomially many. Okay, this is what I discussed and called the k-locality in the context of quantum information. So we can evaluate. This means that if we know how to evaluate these k primes on the fly, so I give you a k and I ask you to return all the k primes that are connected, so to k, then you can immediately compute this E-log coefficient. And in turn, this means that I can evaluate now this expected value of the energy, so this E of theta as I was writing it before, just as the expected value E, calligraphic key, I don't know how to do it with my hands, but over this distribution P of K of the local energy. Okay. So you see from here that this is just the mean over this probability distribution of this object, okay? So this means that if I'm able to generate now samples from this distribution, what I can do is that I can do the following. So I can obtain stochastic estimates, like in an experiment, right? So what you do when you would like to estimate some observable in an experiment? So you do your experiment many times, and then you collect the mean of the quantity that you would like to measure in the experiment. And here it's the same thing. So our experiment will be about drawing samples from this distribution P, and then collecting the value of the local energy on the samples that we've drawn from P. Right. So in other words, this works very nicely. So you first generate a sequence of samples that I'm calling K1, would be the first sample, K2, up to Km. So I have in total M samples. These are all drawn from this probability distribution P of K. Okay. And then after I've generated all these samples, I estimate the expected value of the energy, just saying that this E of theta will be approximately equal to the simple mean of the local energy over these samples. So the sum over the eigens from 1 to m of this E-log computed over this Ki that I've generated from the distribution. Okay. So you know that this object will approach the exact E of theta if m goes to infinity, right? So this is a very well-known law of statistics. And I'm sure that you also know that the accuracy of this estimate is such that the error, if you want, that you make. So if you want the error, the statistical error that I'm doing with this approximation, in if you want approximating E of theta with m samples, let me call this em of theta, in the sense that I'm assuming that. So now this is em of theta, if you want. Okay, my estimate of E of theta. So the error that you make here will go to 0 polynomially, and it will go to 0 like the variance, the square root of the variance of the estimator. So in this case, of the local energy. Sorry, the variance of this variable, this stochastic variable, which is the local energy, divided by the number of samples n. Okay. So are you familiar with this? I mean, have you seen this in the lab courses? Okay, I hope you all know this. Okay. So this is at the heart of Monte Carlo estimates, if you want, of integrals too, because you know that if I increase the number of samples, I can reduce the error like 1 over the square root of the number of samples. Right? Great. So this is the basic strategy and the way how we avoid, if you want, summing the exponentially large system, it's a large number of states. And then, I mean, that's pretty much it, in the sense that, well, not exactly, but I mean, at least we have an idea of the fact that we know how to estimate our loss function, if you want. Now, my E of theta is the loss function that depends on the neural network parameters that I want to minimize, right? So now, the other question that you want to ask is, can I do, for example, gradients of this loss function? So that, for example, I could use all the algorithms that you've learned about, like stochastic gradient descent or any other thing. So this is slightly more complicated than supervised learning, because first of all, you see immediately here that, as I was mentioning already last time, we don't have external data at all in this setting. So all the data is generated from my model distribution P. So P depends on theta, right? So this means that if I change theta, then I'm also changing, if you want, the data that I'm generating from this P of theta, right? So we don't have any external data. So this means that we have also to write down the gradients in a bit more careful way. That's what I'm going to do right now. So let's see if I can write the gradients of the energy, right? So this energy expectation y. Actually, I will not do the calculation in detail, but I will just flash the results. Then I hope that if you want to see the details, they are in the lecture notes that I told you about on Tuesday. But what you can show, if you do a little bit of math, it's not too complicated, that the gradients of the energy, this E of theta, with respect to some genetic parameters, let's say theta k, okay? So this can be written as twice the real part. Now I'm taking everything to be complex because that's the most general thing. The expected value, so the expected value E over this probability distribution P of the local energy of K times something that I call now OK star, that I will introduce in a second. OK star K of actually, let's not call this K, otherwise there's a bit of confusion with what. So let's call this L. So I'm taking the gradient with respect to parameter L in my neural network. Then let me call this OL. So this is the only thing now that will depend on what parameter I'm taking the gradient with respect to in this thing. And then so I have the real part of this minus. So this is like a covariance. So the expected value over this P distribution P of K of the local energy, which is nothing but E of theta if you want, times the expected value of this OP star or L star that I will write in a second. Okay, so what is this OL star, or L if you want, or LK? So this is actually the derivative with respect to parameter theta L, okay, of the logarithm of my coefficients, if you want, of my psi k. Okay. So I remind you that we are parameterizing the psi k with some parameters theta. For example, so the output of the neural network will be my psi k, or in most cases actually directly the log of psi k, as I told you last time. And then this is just, so this O will be just the vector of gradients of the output of the neural network with respect to my parameters theta. Okay, so you can easily compute this O, for example, with automatic differentiation. There are many other tricks that I'm not going too much into the detail of now to compute this object efficiently. But you can see that if I generate samples, so if once I've generated samples from P of K in this step 1, I've computed also the local energy, so this estimator that I wrote before, over the Ks in my data set, if you want, of M samples. Then I can, and I know how to compute this OL for each case. Then this is just the covariance, if you want, between these two random variables, ELOC and O. Okay. So this is essentially the way we measure the gradients, and you will see that this is already implemented for you in codes, so you don't have to worry too much about it. But it's important that you know how this works. Yeah.
What is the star or dot?
The star means the complex conjugation. Yeah. Okay, great. Because in general, as I was mentioning, the logarithm of psi is a complex value. So even if the theta are reals, for example, this all can be complex. Okay, then I mean the learning algorithm is pretty standard once you know how to compute the gradients. Because I mean what you do is that at the beginning of everything you initialize your random, if you want, you initialize randomly your neural network or with any other guess that you have. So initialize the parameters. Theta, let's say at step 0, okay? Then what you do is that you sample from this distribution P of K for this specific set of parameters at step S. So let's say that now I'm at generic step S. Okay, so I generate this set of samples K1, K2, Km. Okay. And then, I mean, at step 2, what I will do is that I will measure, if you want, both the expected value of the energy for this specific set of parameters, theta S, right, as this, again, expected value of the local energy. Okay. And I will also estimate the gradients, if you want, of the energy. Okay, let me just write them like this. And then I have to go to the other page, unfortunately. But step 3 is that you do a gradient descent, as you've done many times now. So this means that you will, for example, I mean, in the simplest SGD, I'm not suggesting that you do SGD, but in the simplest scenario, you can do that your parameters at the next step. Parameter L will go into what you had at step S minus, let's say, eta, then the derivative of the energy with respect to parameter theta. Yeah.
Kind of intuitively, I would expect some gradient of P with respect to theta also.
The gradient of?
Because you said the probability density P also depends on theta, the parameters.
P depends on the parameters, yes. Yes, so actually, so this thing, so okay, so this covariance structure here arises exactly because I'm taking the derivatives of P. So this second part here actually arises from the normalization of P. I didn't do on purpose the explicit calculation. I mean, if you want, we can do it. I don't know, but it's a bit too much detail, but okay, let me just sketch it because I think it's useful. So if we write the expected value of E of theta as the sum of K and K prime of psi star K, then I have the matrix elements of the Hamiltonian, let me call this H K K prime, and then I have psi K prime, okay? Divided by psi K squared. So this is the quantity we want to take gradients with respect to the parameters. Okay, so now what we can do then, so the gradient with respect to parameter theta L of E theta. So you see that here, what I can do is that I can take for example, I can start taking the gradient of psi star here, right? So then I will have sum of over K of, so here I will use the trick that, by the definition, if you want, that the derivative of the log of psi is equal to O, so which means that the derivative of psi over psi is equal to O. So I can multiply and divide by psi here. So that I can write, so this means that the derivative of psi star with respect to theta L is nothing but O star L of k times psi star. Okay. Just think for a second about this. This is a trick that we use a lot of times in this context. Okay, so this would be the first term, the derivative of the first term, and then I have another term which would be the derivative, so k and k prime, sum of k and k prime. Then I would have psi star k. Now I'm taking the derivative with respect. So h, of course, does not depend on the parameters. These are just the matrix elements of the Hamiltonian. Then here I can write this as O of k times psi k, O Lk. Okay. And then there's another term with a minus that is the gradient of the denominator. That's the term that gives you the covariance. But if we focus on just on these two terms, okay, you have to do a little bit of math still, but these are exactly this term here. So this is the real part of this of the expected. You have now. So what you have to do is that you have to multiply and divide by. Okay, so for example, if we focus on the first term, so this is sum over k and k prime of OL k star psi star k h k k prime psi k prime, okay, divided by sum of k psi k squared. So this is the first term that we have in that summation. So this we can write it, just by dividing and multiplying by psi k at the numerator. So we can write this as sum of k of psi square k. Right, I just multiply and divided, and now I will have OL star k h k k prime, and then I have to divide. So I will have psi k prime over psi of k. Okay, so you see that here I've reconstructed the same form that I had before, right? In the sense that I have means averages over psi squared. So this is my P of k. And you see that also here, sorry, there's a sum of k prime, of course. You see that this sum of a k prime of this object here, hkk prime, this ratio is exactly the local energy as we defined it before. So you see that what I've written here is the expected value of O star times the local energy. Okay, so this is the expected value over this P of O star L times the local energy. This is the first term. Then you will have the complex conjugate. This will give you twice the real part, and this is this part here. And then the denominator gives the other. Okay, I will skip the full derivation, but you see, I hope, where it comes from, where everything comes from. Okay? Great, thank you for the question. Now, the small and slight detail that I cannot give you, I mean, I cannot tell you too much today about is the fact that how do we generate these samples? So how do we generate this k from this P of k, right? So given that I know how to compute this P of k, the unnormalized P of k, how do I generate samples from this P of k? So this is the goal of Markov chain Monte Carlo. Unfortunately, yeah, the lecture that you were supposed to have was moved. But let me just give you a very rough idea. So Markov chain Monte Carlo is one possible strategy to do step one, if you want, in the previous so step one in the previous stochastic estimates slide, if you want, was to generate a lot of samples from this P of k. Okay, so how am I going to do that? Well, one, if you want, Swiss knife way of doing that, knowing that P of k is this psi of k squared divided by some normalization n that I don't know how to compute. So I just know how to compute, if you want, the numerator efficiently, which is the output of my neural network, but I don't know the normalization of the wave function, that in this case is different from one. Well, then what I can do is that I can, again, Markov chain is a way to deal with that, because essentially it's a way to generate a sequence. So that's why this is called a chain, because I can generate a sample starting from the previous one, right? So it's a chain of samples where K1 will lead me to the next sample, K2. K2 will lead me to the next sample, K3, up to the last one, Km. Okay? And the way I do this is that I have some, if you want, global transition kernel, global transition probability that I call calligraphic T in here, that will give me some probability of going from the given, if you want, K, Ki at the step I, if you want, in this Markov chain, to the next state, Ki plus 1. Okay? So the idea is that I am now, I am at step I, so I have some sample K. So K, again, I remind you, is just a sequence of plus or minus 1 that is what I want to sample from. So these are the kind of things I want to sample from P of K. And then I can ask, how can I go to another sample that is approximately distributed or is exactly distributed from my P? Okay? So to do that, I will use a global transition kernel. So this is just a probability process, if you want. So I have a probability of going to the next step. So the most, one of the most famous way of designing this global transition kernel in a way that you sample from your P of K is to satisfy what is known as the detailed balance condition. So essentially, you have to design this global transition kernel in a way that the probability of going from K to K primes times the probability of being in K should be equal to the probability of being in K prime times the inverse process. So the transition for the inverse process. Okay, so this is known as the detailed balance. So the balance condition, if you want, or the detailed balance condition. So if your T satisfies this probability, this condition for your target P, so this is really my target P here, then you can show analytically that these Ki's will be distributed according to my P of K. Okay. So actually, let's do like that. So how many of you have seen this before so that we don't repeat these things twice? But okay, so most of you. But essentially, this is the idea that if I'm able to design a global transition kernel that satisfies this detailed balance, then I can also sample from P. You will see all the details of this in the next in the specific lecture where you will see this done in detail. But what I just want to tell you about is the most famous way to do this is the Metropolis Hastings method, or algorithm, which, by the way, is one of the most used computational methods in all history of science. So you should really know about this method. And so the idea of this Metropolis Hastings approach is that you essentially write this, what I call this global transition kernel that brings you to a K to another K prime. So this transition probability, if you want, this global kernel as a local transition kernel that I will write with this other T, not calligraphic, but bold T, let's say, of going from K to K prime. And this is what we call a local transition kernel. So this is a local transition kernel or transition probability. I'm using the word kernel, but it's clearly, a synonym in this context of probability. And this is a global transition. This was what I wrote before, so the global kernel. Okay? So we factorize this global transition into a local transition kernel times an acceptance probability, A of going from K to K1. Okay? So this is now my acceptance probability. Okay, so you have to think that this local transition kernel is something, so it's some transition probability that acts only on few degrees of freedom, and that I can correctly normalize. So, for example, if I have my sequence of plus or minus 1, what this local transition kernel might do is that it picks one random spin, one random 0, 1, and it flips it. Okay, so it suggests that the next K prime, if you want, is almost identical to K, but for a single bit that is been transformed into -1 if it was +1 before, and vice versa. Okay, so that's why we call this local, because it changes only one of the elements in my sequence of bits or in my sequence of Ks. Okay, so it's not something that acts globally on the full set of configurations. Okay, maybe you've seen this in the context of the easy model, right? Have you seen it in the context of the easy model? Yes. So in that case, when you sample from the Boltzmann distribution, you pick a random spin, you flip it, and you accept or reject that move. And this is exactly the same thing here. The only difference is that we are not sampling from the Boltzmann distribution as you do for the easy model, but we are sampling from this generic P that is parameterized by a neural network. Okay, so this is the main difference. And then, I mean, you can show what Metropolis and Hastings actually showed is that this acceptance probability. So the algorithm is the following. So you first propose with this local transition kernel a change in your K, right? And then you accept it or not with some probability A. Okay, so this is the main idea of this approach. And then they show that if you satisfy these conditions, so if the acceptance probability is given by the minimum between 1 and the ratios of the two probability distributions you want to sample from computed at K prime and at K, okay, times these local transition probabilities, first to go from K prime to K and then the inverse process. Okay. Then if you satisfy these conditions, so if your acceptance has this form, then you will satisfy detailed balance, and then you will sample efficiently from, not efficiently, you will sample provably from the original distribution. So again, I'm not going into the proofs of this, but you will see them next week. I just wanted to write down the algorithm because it's important that also for the tutorials later today you will need it. But the major contribution, the major, if you want, and really deep thing about this algorithm is that to compute the acceptance probability, which is the only thing you need to do in this algorithm, in a sense, you only need the ratios of probability distribution. So you don't need the absolute value, if you want, of the probability, but you only need to compute what is the relative probability, in a sense, between two states, K and K prime. So this means that the unknown normalization that we had here will completely cancel out when we take these ratios. Okay? And you see now that these ratios will be just if you want, in our specific case, the psi of K prime of theta over psi of K theta for some value of the parameters theta squared. Okay? So this means that if I have a neural network that knows how to compute for me psi K theta for an arbitrary K, so it's just, this would be just again the output of your neural network, I can also compute this ratio efficiently, and that's the only thing I need to do in order to compute this transition, this acceptance probability. This because I've chosen this transition probability T to be local, so I know how to normalize it and I know everything about it, so I know how to compute also these values here if you want. Okay? So actually, in the simple case that I told you about, where I take one of my bits and I flip it, this ratio here would be equal to 1 because the inverse, the probability of doing the inverse, if you want action, is exactly equal to kk prime, right? Yeah. So this is that. So this is maybe what you see in the normally as this is what is known as the metropolis argument. So where you don't have these correcting factors here, but you only have the ratio of the probabilities. So that's maybe what you see in the more elementary courses. But if your transition probability is not symmetric, which can happen, then you have to correct it with this factor. Okay.
So here K and K dash can be two arbitrary states, right? Doesn't have to be like locally.
So K and K prime can be two arbitrary states. The only requirement is that this local transition kernel is some transition probability that you know how to normalize, if you want, or that you know how to generate samples from, right? So if you want, we have reduced the problem of sampling from P, which is hard, from to the problem of sampling from T, which is now a much easier task.
If you only run local transitions, then how will you ever have global transitions? I didn't get this kind of distinction between these two.
Yes. So the idea is that we right. So if you want the Markov chain is a process where I go from state K1, K2, K3, etc. through some probability distribution, and this is what I call the global transition kernel. Okay, but this is different from the local one because the total process is first proposing and then accepting or rejecting. So this is my global transition probability. You see? Okay, so it's global in the sense. Global in the sense that it's global. It's for the Markov chain, right? So you see that's what I wrote here. So you see this is what I call maybe global is a slightly misleading name because it's still a local thing. But let's say global in the sense that it acts that you know it pertains to the total Markov chain and not only to this local transformation. Okay. Great. Okay, so this was my slide, just an idea to give you a rough idea of this approach. But so in practice, if you wanted to implement this, it's very easy because what you do is that you start with some. So you start your Markov chain if you want at step 0, right? Typically, you start with some random. Yes.
Just a question regarding the transition kernels. So, is there any general design principle how to use them, or only if it doesn't go too far?
Right. Yeah. Yeah. No. So there are many design principles. Let's say one good idea, for example, is to take the off-diagonal matrix elements of the Hamiltonian. And this can guide you in how to choose the kind of moves if you want. Or if we go back to the example of the transverse field Ising model that we did last Tuesday, in that case, the off-diagonal matrix elements, KK prime, if you want, were those where we flipped one spin, or were flipped one of the spins, right? And you can think of this process as also something that we can do in the Markov chain. So this is, for example, a systematic way of designing this transition probabilities. In general, there's no guarantee that this will be ergodic. I mean, you have to prove it, but okay, in the case of spin flips, it is ergodic, but you have to make sure that this is ergodic, and also there's no guarantee that the convergence will be fast or there will be any convergence in polynomial time. So this is one problem with Markov chain that we cannot solve easily. Okay, but if you are smart enough, or I mean, if you do something reasonable, you typically have, and there are ways to check that convergence has happened. And I don't want to do that, but you will see that I think in the other lectures. But the approach is very easy. So as I was mentioning, when you do this Markov chain, so you start with some random. Random means that you, I don't know, for example, you could draw it from some uniform distribution in between all the possible values of this K. which would be, for example, in between 1 and 2 to the n. So imagine that k is just an integer between 1 and 2 to the n, right? Which is, again, equivalent to having a vector of plus or minus 1, right? Then you just start your Markov chain with this random state, and then you generate with this local transition probability some k of I plus 1, right? So you generate this k prime. So this means that, for example, I take this k that I've generated, that I'm currently sitting at, and for example, I can pick a random bit and I can flip it. Okay, that's completely acceptable. Then you compute this ratio. So this ratio that I discussed before will be this p of k prime over p of k times these t factors. Again, in most cases, you don't have to worry about these corrections because they are symmetric. So the probability of doing this inverse transition will be equal to the direct transition. But in general, you have to, so let me put them like this. So in general, you have to think if your t is symmetric or not, but otherwise there's no problem. And then the third step is to, you just, so this is your proposal now, your proposal step. I'm proposing some k prime, okay? And now the actual action will be to either accept or reject this k prime. So to either accept or reject, you draw some other random number xi uniformly in 0, 1, uniformly distributed. Okay. And if this random number xi is smaller than r, then you accept your you accept your move. So which means that the next state in the Markov chain is equal to what I propose here. So this k prime. Okay. If instead this xi turns out to be larger than r, or equal, I mean, it doesn't matter too much, then the next step will be the same. So I will reject the move. So it means that the next step in the chain will be the current state. So I will not update, if you want, the next configuration with what I propose, because that's not good enough according to this criterion. And then I will stay with the current configuration. Okay. So and then with this approach, repeating it m times, if m is the total number of sums that I want, as before, then I will generate this chain of events, chain of sums. Okay? Great. So how much time do we have? Still 45 minutes, right? Okay. Something that I want to maybe quickly mention to you is that Markov chain Monte Carlo is not the only, by no means, the only way of sampling from your models, so from your P of K, but it's again the Swiss knife thing, right? So I work in Switzerland, and I told you about the Swiss knife approach. There are less universal approaches that are tailored instead to specific models of wave functions or neural networks, if you want, that we are using. So just to give you an idea, for example, there is something that we call autoregressive quantum states. So I know that you've been given an introduction to maybe deep generative models. Is it true? They've seen some. Okay, great. But let's forget about that for a moment, and let's stick to the math. So what we call autoregressive quantum states are, if you want, a set of neural network models for wave functions that are designed especially with this task in mind of being able to sample efficiently without doing Monte Carlo from this P of K. So if you want, since we have a lot of freedom in designing if you want, the neural network that we are using to represent our P of K, we can also, if you want, design a special neural network that we know how to sample from exactly, right, without doing Markov chain, right? So this is the basic idea of these more modern approaches. So this will allow us to perform, if you want, exact sampling, meaning that we don't have to do this nice but not provably efficient, if you want, the Markov chain approach. And the main idea of this kind of parameterizations is that you will now write, if you want, your psi of k, so your model wave function. Okay, that I remind you, I mean, we can think of this as a psi of using the notation we used last time, so sigma 1z, sigma 2z, sigma nz. Okay, so again, each of these sigma 1 is plus or minus 1, and k is the binary representation, if you want, of these vectors, this vector of plus or minus 1. So the idea is that we write this now as a product that goes from 1, for I that goes from 1 to n, of some phi I, some other functions that I will write in this form, sigma iz given sigma I minus 1 z, sigma I minus 2 z, sigma 1 z. So if you want, just take this at face value mathematically. What I'm doing is that I'm writing a model for my psi of k that is the product of some function, right? That of n function, if you want, that I call phi here. Where each of these functions has the property, maybe it might sound bizarre, that such that, for example, phi 1 would depend only on sigma 1, would not depend on the other values, but would depend only on sigma 1. Okay, phi 2 would depend only on sigma 2 and sigma 1, but not on, let's say, on sigma 3, sigma 4. So only on the previous variables in this special ordering that I'm choosing. Okay, so phi 4 depends on phi 4, phi 3, 2, and 1, but not. Okay, I hope it's clear. We can generalize this. Now, and also I choose these phi's in such a way that the sum over, if you want, all the possible values of sigma. So let's say of sigma that takes the two possible values, the plus or minus 1, of phi I sigma given an arbitrary set of let's say sigma I minus 1, I mean sigma 1 squared, this is equal to 1. Okay, so if you want, I choose by design that my phi i's are normalized in this way. Okay, so they sum up to 1 when I sum on the first input variable of these functions, only on the first one. Okay? So if I satisfy this condition, then you can show that the resulting psi ok is normalized. So which means that if I sum now from k from 1 to the n psi k squared, you can show that this is going to be equal to 1 as well. Okay, so we have a nice way of normalizing the full wave function just by normalizing what we can call quantum conditional probabilities. I mean, if you want, because these kind of parameterizations resembles what you do with probability densities, right? So with probability densities, you know that you can always factor them, write them as a product of conditional probabilities, right? Of variable 1 conditioned on nothing, variable 2 conditioned on variable 1, variable 3 conditioned on 2 and 1. This is essentially what you do with probabilities. But you can extend this concept to probability amplitudes. So these psi's now are complex, right? So there is nothing attached to phi in terms of, if you want the probabilities, it's the square of these objects that are probabilities actually, but not the phi's themselves. So you can generalize this, the math works, and we've done this in 2020. And I mean, the reason why this is interesting is because now if I write P of k, which is just the square of this psi, right? So I remind you that P of k, the thing that we want to sample from, is the square of the psi divided by normalization, but in this case the normalization is 1, so we are also in yes.
Is this understand. So I see how it recovers any probability distribution of the configuration space. Does it also recover any wave function?
Yeah.
Could be, yeah, it is.
Well, any depends on. So if your phi I are expressive enough, yes, you can write an arbitrary psi in this form.
Okay.
Yeah. But in practice, you see that now psi k squared. Now what I should do if I want to compute this probability distribution is that I have to take the square of this expression here. But the square of that product, it's actually the product of the squares, likely. So I can do pi of 1 to n of this phi I squared of sigma I z. Okay. So now you see that indeed, in this case, now the probability distribution I want to sample from takes exactly the form of a product of conditional probabilities. Because now these objects are, these phi squared are actually conditional probabilities. So there is a beautiful strategy to sample now from this P of k, which is essentially I draw the first spin according to phi 1 squared. So I draw sigma 1 z according to phi 1 of sigma 1 z squared. So again, the first phi 1 depends only on sigma 1. So this is, if you want, the function of, I mean, this can take only two possible values. It's very easy to sample from this. And then, I will draw sigma 2 according to the conditional probability of sigma 2 given the sigma 1 that I just draw, right? So, and this is exactly this what I call phi 2. And so on and so forth. So you can generate in a sequence all the spins one by one, and the sampling is exact. So there's no Markov chain, no acceptance involved if you want. Everything is accepted. And all the samples are actually uncorrelated. There's no correlation, which is also an issue that you will see more in detail during the other lectures when you do Markov chain. Okay. So this is just to give you an idea of how this kind of things works. If some of you are curious to read the details of these complex valued autoregressive things, we did it in this work in Physical Review Letters a few years ago. Okay. Yes.
Kind of reminds me of Gibbs sampling.
So Gibbs sampling depends, yeah, in the context of Boltzmann machines, maybe, I don't know where you, right, so, but that's a special case of Markov chain, actually, you can see it like that, yeah. So there's still a correlation between samples if you do Gibbs sampling. Here, this is called ancestral sample, ancestral, like your ancestors, right? Ancestral sampling. Because essentially, so the idea is that your ancestor here is a sigma 1, right? So given your father, your mother, I don't know, you have to draw sigma 2, which is a son or daughter of sigma 1, and then you have to, the grandson and granddaughters of sigma 2 of sigma 1 are sigma 3s, right? So it's like a genealogical tree, right? That you are going through, starting from the first ancestor and then to the last one. That's why they call it like that. I mean, don't blame me.
Sometimes it's still approximate, right? Like, because this phi I.
No, this is it's all exact.
But
So
your phi I's are not like.
No. Here I'm assuming. Okay, so sure. So I'm assuming that the phi i's are given. They have some functional form. For example, you can parameterize each of them with a neural network, and it's easy to normalize them in a way that they satisfy this property. Sorry, this property here. This is just a last normalization layer that sums over one variable, so it's very easy. Okay. So if I'm given this parameterized form, then I can sample exactly from this psi. Of course, I'm not saying that this corresponds to the exact ground state. You have to find that, right? So at the end, you still have to do this, the actual learning approach, where you have to initialize the parameters that appear now in all these phi i's, sample with now this exact sampling. So this is where you are safe because you don't have to do Markov chain at least. Measure, compute the gradients, update, resample, measure gradients, resample. Okay, so you see why this is more expensive and a bit harder than quite harder than supervised learning, because you don't have data. You have, at each step of SGD, you have to regenerate new data. Good. Great. Now, in the last 30 minutes, I would like to tell you. So first of all, I mean, if you have questions, don't hesitate to ask, because I know it's a lot of material to digest, and we can make this also more interactive if you think that there are things that you don't understand at this point. Yes.
So perhaps for generating these conditional probabilities, sampling in this ancestral way. So,
yeah.
What was your parameter? So did you really use auto-regression, or did you use something more?
Yeah. So okay. So the thing that I didn't mention here. So the nice thing that you can take and that you can do is that you take a different, let's say, feed-forward neural network or whatever that represent each of these phi I, right? So you could take n different neural networks, each of which represents one phi I. You could do that. That's a possibility. There are smarter way of doing this. So you take one neural network with n outputs, and each of the outputs correspond to this to one of the phi i's. For example, the first output you say is phi 1. But if you do that, you have to make sure that they satisfy this conditional dependency. So this means that, for example, if I take a neural network like this one, so we have now sigma 1, sigma 2, and I want that the output of this neural network is, let's say, phi 1, phi 2, phi 3, and phi 4. Okay, so I need to have that phi 1 depends only on sigma 1, not on all the rest, right? So this means that I can do all the things I like, but there should be only a connection between, if you want, sigma 1 and phi 1, not you have to cut, if you want, all the path that would connect, for example, sigma 4 to phi 1 to the output. Okay, and the same thing for phi 2. I mean, you can put also intermediate layers, you can do whatever you want, but you cannot have that there are incoming connection from sigma 3 and sigma 4. They can come only from sigma 1 and sigma 2. This is known as autoregressive structure in PixelNet or in other structure. I mean, yeah.
Also, perhaps relatedly, so I guess then if you choose the standards, you have to put in a bit of prior knowledge into the correlation vectors in your system, just like how does this turn out to be? So depending on your phase, your NF, so do you like really make these probabilities depend on all the prior spins, or do you say, okay, I'm mistaken, you have to let the sites away?
Yeah, so indeed, that's a good question. So if you have a phase that satisfies this area law of entanglement that I briefly described the other day, so if you want, if you know already that in the ground state, your spins that are here are not correlated to the spins that are on the moon, and typically this is a good approximation, right? Then you can say, listen, forget about putting direct connections anywhere between the spins here and the spins on the moon. I can cut a lot of this, and I simplify my model. So this is the sort of prior knowledge that you can put. For example, locality is an important prior knowledge. However, there are unfortunately interesting phases of matter where you have very long range correlations, and there you cannot do this kind of for example, at phase transitions. Okay, so the last thing that I want to tell you about, so that you have an idea of other kind of problems we can solve. is how can we learn not only ground states but other things, right? So I mean, as I was mentioning, ground states are very important, but they are not the only thing that we want to do in quantum mechanics. No, so I'm thinking actually I will have another lecture next week if I'm not mistaken. So it's great. So it's time. It's good because then I will have time to tell you data-driven approaches next week. Okay. So for this week we focus on the non-data-driven in the sense that everything is done on the basis of the Hamiltonian and there is no external data. Next week we will see how we can use data from experiments, but that's another story. Okay. So, but for today, another application that is non-data-driven is, for example, learning the dynamics of quantum systems. Okay. So if you want, the other equation that I didn't tell you about yet, but that some of you already know, is the time-dependent version of the Schrödinger's equation. So I've told you about the ground state, so the time-independent, so-called ground state, this eigenvalue problem for H, which is the so-called time-independent Schrödinger's equation. But the time-dependent Schrödinger's equation is essentially this equation for the vector psi. So essentially, the idea is to so if you have your state, I'm trying to use the same notation. Okay. So essentially, in general, my quantum state can depend on my vector, if you want. The coefficients of my vector will evolve in time because of some physical phenomenon, and the time derivative of these coefficients will be given by the application of the Hamiltonian onto the state at time t. Okay. So if you want, we can also write this, for those of you who are not familiar with this notation, we can say that I, D, and the T, if you want, the sum of the K that goes from 1 to N of these coefficients, CK, if you want. Sorry, there's no dot because I already put the time derivative there. So CK of T, okay, this should be equal to, so we can also write this as so the sum over K, sorry, just forget about this. So sum over K is equal to sum over K prime of C K prime of T H K K prime. Okay. So you can think this about this as again a first order differential equation for your coefficient CK with some initial condition CK of T equals 0. Okay. So my vector starts with some given initial condition, and then at the next time step, if you want, the next step, these coefficients CK are changed according to the action of this Hamiltonian. Actually, this is the definition of the Hamiltonian in a sense. It's the object that drives the dynamics of quantum systems. Okay. Now, the problem so what we would like to do is that we would like to find a good approximation for this CK of T, right? So we would like to, if you want, try to approximate this again, this CK of T with some neural network, for example. So we would like to have some f of K and I don't know, of time in general. Okay, so I'm not writing the dependence yet on the parameters, but let's say that I want to find a neural network that, given the time t, can compute for me the amplitudes at that time. Okay. So the problem now is that we cannot use just the standard variational principle that I wrote before. So the fact that we can minimize the expected value of the Hamiltonian, right? So we used this before when doing the ground state. We use the fact that this is strictly larger or equal than the exact ground state energy. We simply cannot use this because there is no dynamics involved in this principle. So you will find just one state that will not evolve with time. Okay? So we have to find an alternative to this static variational principle, this is what we can do through what we call the time-dependent variational principle. Okay? Now, this is something that I'm pretty sure you haven't seen in undergraduate studies, I mean, unless I'm mistaken. But let me just guide you a little bit through this in some high-level detail, and then you can see that it's not too complicated. So the idea is that now what we would like to do is that we would like to push, if you want, the time dependence of the state into some time dependence of the variational parameters, so of the thetas. Okay, so if you want now, I will consider time dependent variational states, or if you want, time dependent neural networks. Okay. So if you want, now what I will do is that I will try to approximate my, if you want, state phi of t, my exact state that satisfies the exact Schrödinger's equation, with some approximate psi, so a variational state, so for example, a neural network that will depend parametrically on some parameters that depend now on time. Okay? So if you want, what I'm doing now is that I'm saying, consider a neural network and make the parameters in this neural network depend explicitly on time. Okay? So now, if I know how these parameters evolve in time in an optimal way, so in a way that they match as close as possible phi of t, then I can try that I can reconstruct, I mean, almost by construction, the dynamics of my system. Okay, so this is the task that now, yes.
I don't understand the notation.
Yeah, sorry, maybe because I keep switching between brackets and vectors. But okay, so let's say that if we write this in vectors, right? So the reason why I'm using cats now because it's easier. But okay, so let's do like this. So let's call because there are two states here. So okay, so let's call let's call the exact coefficients of the state phi. Let's call them actually gamma. Okay. Gamma k. Okay. So now think that the gamma k's are the exact coefficients of the state as they evolve in time. Okay? Now, what I'm trying to do is that I'm trying to approximate, if you want, this gamma k with some neural network. Okay, so then and I will call this object ck now, ck of t, if you want. Okay, so you have to think that there are two different vectors, the exact one and the approximate one. It's this is the tricky part that you have to keep in mind. So again, so if you want, in this notation here, once more, indeed, this is gamma, if you want, component-wise, this is gamma k of t, and I want to approximate this with some ck of theta of t, okay? So the output of the neural network that depends through theta, and in turn, theta depends on time, so there will be some time dependence in these parameters, okay? Now, what's the idea? The idea is that we use what I was anticipating. It's known as the time-dependent variational principle. This was invented or described by Dirac, the same guy of the Bride the Cat. And Frankel, Dan Frankel was also one of the fathers of computational quantum mechanics. I think it's the same, actually. I'm not sure, but anyways. So the main idea of this variational principle is that so it works in this way. So I imagine now that I am at time t. Okay. Now, at time t, you can think that I have my exact state that again, I can think it's like a vector in this huge highly dimensional space, but think that I have now my vector. So I'm writing it in 2D because I cannot do a 2 to the n dimensional plot. But imagine that at time t, I have my initial state phi of t. Okay, so this is again like a vector, right? Then what happens? It happens that there will be two relevant vectors for our story. There will be a blue vector, which will be the exactly evolved state at time t plus delta t. So now I'm reasoning in terms of differentials, so in terms of small time variations. And this, I will call this phi of t plus delta t. Okay? So this is the exactly evolved state because of the action of the Hamiltonian. Okay? On the other hand, I will have a family of vectors that I write now in red that will be given by the action by the fact that I'm updating my parameters theta in a way that they, at time t plus delta t, they are not what I had at time t, but they are slightly different. Okay? So these are my psi, if you want, of theta of t plus delta t. Right? So you see that depending on how I update, if you want, my theta, so the next step, I can move a little bit this red vector in this plane because I might change more parameter 1 or more parameter 2, and this will amount to changing a little bit the direction of this red vector, right? So the main idea of this variational principle then is that I can minimize this distance. So the blue vector is fixed if I fix delta t. The red vector can change depending on how I change the parameters at the next step in time. So what I can do is that I can find the optimal change in the parameters that minimizes the distance between these two vectors. And this is the optimality principle in this context. And you have to do this at each time step. Okay? I hope that this is clear because it might be confusing when you see it for the first time. So if you do it slightly more mathematical, then we have two states. So we have state 1, which is my initial state. So do you want me to do it with cats or with vectors? I don't know. Let's do it with cats, if you don't mind, because it's slightly easier for me. Okay. But anyways, so I start with some state phi of t, which is my initial condition. So this is the black state here. Okay. So this is phi of t. Now I assume by construction that this is equal to my also variational state, my neural network at time t. Okay. So if you want, in all of these constructions, I'm assuming that the initial state is exactly parameterized by the neural network. And then the error is made only when I move to the next step. Okay, so this is the best we can do actually. This is a local variational principle. Now, at the second step, then I have two, if you want. So what happens is that I will have two, if you want, two states. So I will have a state A, which is the state that I wrote in blue, and which is given by the action of the Hamiltonian. So if I discretize time, it will be given by the identity minus I delta t h, so this operator, applied on my initial state phi of t. Okay? Just think a little bit about this. It's just the discretization of this for a small time step delta t, right? So at the next time step, I will have phi of t plus actually minus I. I put the I here. So it's minus I h times the old vector. Okay, just a discretization in time of the Schrödinger's equation, first order differential equation. So this is my blue vector. Okay, so maybe I can also put it in blue so that it's clear. The vector A. Then I have vector B, which is instead the vector that I get if I modify the parameters in my neural network. Okay. Now, you can show, I mean, it's relatively simple math, but this is given by the following expression. So it's 1 plus delta t, the sum over L, it goes from 1 to the number of parameters that you have in your neural network of this O of L that I will write in a second, but we already saw them before, times the time derivatives of your variational parameters acting on your state phi. Okay. Well, now, I mean, essentially, these OL are again is a diagonal operator actually, and these are the objects that I introduced before. So these are the derivative with respect to theta L of the logarithm of the wave function, the logarithm of psi k. So okay, I didn't really derive equation B, but I mean, imagine that I sit at time t, and then I have to do a first order, you know, essentially Taylor series in these parameters, saying that, assuming that at the next time step, the parameters go in theta plus theta of t plus delta t times theta dot of t. Okay, so that's where this expression comes from. I'm not doing the exact derivation, but you see now that the state B, that is the red state that I had before, as I was anticipating, depends parametrically on the time derivatives of my variational parameters of this theta dot. So these are the only degrees of freedom that I'm left to work with. Okay, because the state phi is fixed. So if you want, the parameters theta of t are fixed. The only thing I can play with are not the parameters themselves, but the changes in the parameters, right? So that's why this is a bit of a meta concept with respect to the standard optimization that you see. So you don't optimize the parameters themselves, theta of t, but the change in the parameters, which are this theta dot or delta theta, if you want. And now what we are left, the task that we are left to do, is to find the maximum with respect to this theta dot of L of the distance, if you want, the overlap, or between, or if you want the minimum, it depends how you define it, but typically we work with the maximum of the overlap, what we call the overlap between these two vectors. So this A and B squared divided by AA B. Okay, so if you are not familiar with this concept, this is just, if you want, the projection of this vector A on B. Okay, so I want to maximize the projection on one vector onto the other in a way that you know, they're as close as possible. Yeah, so it's clear that this is a good definition. You could use other metrics, but this is the most natural in quantum physics. And now, if you maximize this object, which will depend parametrically only on these theta dots, you will end. So if you write down this object explicitly, I'm not going to do that, but if you write down explicitly, you can find out that this is just a quadratic problem in these theta dots. So you can find the optimal values of this theta dot just as a solution of a quadratic problem that we know how to solve very nicely. So, and I just write for you the final solution. So we know that the optimal theta dots satisfy this equation. So they satisfy this sum of L prime of a matrix that I'm going to write in a second as L prime. Theta dot of L prime must be equal to what I call G of L. Okay. So let's just look at for a moment at the mathematical structure of the equation that you have to, if you want to solve at each time step to find these optimal objects. So this is just a quadratic equation where you have a matrix S and a vector here. So you just need to invert, if you want, this matrix multiplied with this vector, and you will find the optimal solution of this system. Okay. So what are these matrices? Again, they come from the math when you do this optimization analytically, but they're pretty nice. So essentially, so G of L is actually by accident or not so by accident related to the gradient of the energy that we wrote in the previous slides. So it takes exactly the same form. So it's the expected value, the real part of the expected value of this O of L star times the local energy minus the expected value of OL star, the expected value of the local energy. Right, so this is exactly, I mean, minus a factor of 2, the same object that we found when we wrote the gradient of the energy. Okay, so it's in a sense related to the gradient of the energy. This S matrix instead is something that you haven't seen before, and takes so this form. So it's the real part of so the derivative of my state with respect to theta L overlap the derivative of my state with respect to theta L prime minus the derivative of psi with respect to theta L times psi, and then I have psi de theta L prime. Okay, and it turns out that you can estimate this object simply as the real part of the expected value, again, over the usual distribution. So I'm not even writing that it's, okay, I'm writing it's over P of this O L star O L prime minus the expected value of O L star O L prime. So if you want, this is the covariance matrix of these O derivatives. Okay, and this is known in the community, if you want, in quantum physics, as the quantum geometric tensor. Or quantum Fisher information, or Fisher matrix, actually. Fisher information matrix. Okay. Maybe some of you have seen this object in the context of classical probability distribution. So this is if psi was not a psi, but a probability distribution, so a real valued object that is not complex, then this would coincide exactly, apart from some small factors, with the classical Fisher information matrix. If you generalize psi to be a complex valued probability amplitude, you end up with this other object. But these are related, and this is more general of the classical one, of course, because here we have a complex object. And they all contain information on the metric of your variational space. There is a beautiful connection between, for example, the metric induced by your variational parameters and this object, this matrix here, that I cannot go too much into the detail today. Yes?
Here the expectation is computed with respect to
the same distribution, P of K of theta of T now. So I will write down the resulting algorithm in a second so that it's more clear. But, yeah.
That also depends on time.
Yes, exactly. So I will do this. So now you see we are not now we don't have any more an SGD-like approach where at each step we compute the gradients and minimize stuff, right? So here each step corresponds to a time step. So I go from time step t to time step t plus delta t, t plus 2 delta t. So these are my discrete steps that would correspond in the other case to the SGD steps, right? So if you want, I can write down for you the resulting approach, which we call the time-dependent variational Monte Carlo. So again, so you initialize now your parameters theta at time t equals 0. So this would correspond to taking some initial state that is your neural network at time t equals 0 and that you want to evolve in time. Okay, so I can take either a physical state, for example, I don't know, the ground state of some Hamiltonian, or I could take a random state. It's up to you. So this is just the initial condition that you have to provide to Schrodinger, otherwise you cannot evolve the state in time. And then and then what you do subsequently is that you, as before, you sample. So at each time, what you do is that you sample from your pk of theta of t, right? So now my parameters will depend on time. So now I'm sitting at time t, I have some fixed value of the parameters, I sample from this p of k, which would be proportional once more to psi of k and theta of t. I'm not writing t again squared. Okay, so I can do Markov chain, I can do exact sampling, whatever you were doing before. And then you do as before. So you measure properties, so you measure quantities over this distribution, so over the samples that you generated. So you will measure this G of L that I wrote here simply as a covariance of these objects that you can compute efficiently again over the samples. And you will measure also this matrix S. Okay? Yes, 2 minutes. Yeah, great. Right? And then at the first step, so now that I have stochastic, so I have some estimates of this G and of this S, I solve this linear system that I wrote before for you. So I solve this linear system that was here, which is you see, so this linear system, which is this S, if you want, matrix applied to this vector of thetas, theta dot, right, is equal to G vector. I mean, these are, okay, sorry, it's a mess. Okay. So you see, I just have a linear system where I have a matrix S, a vector of unknowns theta dot, and this G is known. So I have to invert this system and find the theta dots. Okay. And then, I can use my favorite OD integrator, Runge-Kutta, no, don't use Euler, just use some higher order integrators to go to the next step. So, so the simplest thing you could do is Euler, but don't do it. So you could say that theta, at step t plus delta t, my parameters are equal to theta of t plus, so the F parameter plus delta t, so my time step times the theta dot of L that I just found by inverting the system. Okay, then you go in time, so you have advance until you reach the final time. Of course, you accumulate errors, but that's life. Okay. Now, you might be worried that if I have 1 million parameters, solving this system for a matrix that is 1 million by 1 million might be complicated. And indeed, I mean, I'm not going into the details, but we don't do that. So we don't actually estimate this full matrix by entry, because it would be too expensive. You would have 10 to the 12 elements if I have 1 million, if you want parameters. But we actually use an iterative approach where we only need to estimate how we apply this matrix on a vector. Maybe you've heard about this the conjugate gradient method to solve linear systems. So in that case, you need to know only how to apply this matrix on a vector. And that can be done with a cost that is only linear with the number of parameters. So in a sense, we go back to the complexity of solving for the ground state where you have to do only linear operations in the number of parameters. Great. So I think that's it. Thank you.
Thank you.
Okay. So welcome everybody to the last lecture or tutorial, say, of this day. So now the speaker is Javier. Javier is a PhD student at NYU and at CCQ, so where we are. He supervised Antoine George, our director, and Giuseppe. So this is why Javier is an expert of quantum state and application of essentially this tutorial will give us an overview on the NetCat, which is kind of the software that make in practice what we have learned from Giuseppe lectures. Okay, so we really look forward to your presentation.
Thank you very much. So yeah, as Domenico said, yeah, I'm going to be doing a little tutorial on NetGet, which is an open source Python library to do this variation on Monte Carlo type of optimizations of neural network quantum states that Giuseppe's group has been developing. So I mean, they have their own webpage, which is actually, and with the official documentation of the library, which is very nice right now. And of course, you can also access their GitHub repository and directly clone the repo from there if you want to. But it's open source and very well documented. So, and of course, they welcome contributions if you want. So yeah, if you are interested, definitely go ahead. Okay, before I begin, I would like to first tell you that please, if you have any questions, interrupt me. I think it will be much better if we make this a little bit more interactive. And the second thing that I wanted to ask is how many of you are physicists? Okay. And the rest, what other fields do you come from? Computer science mostly. Okay, okay, great. Okay, so the way that I'm going to be talking about quantum mechanics is mostly from a linear algebra perspective, kind of similar to what Giuseppe has been doing, but maybe even focusing a little bit more on vectors and matrices and so on, and demonstrating here with a simple Jupyter notebook how we think about these things. Okay, again, so you can pip install NetGet, which is very convenient, of course. Now, NetGet is using as a backend JAX, which is a machine learning library, which it's fantastic to do automatic differentiation, compile your Python code, so then all of the linear algebra that you're doing under the hood is properly compiled and so on. So now, as I'm going to be running stuff on my laptop, I'm going to let JAX know that I'm going to be using the CPU, not the GPU, because JAX, if it detects that there's a GPU, it will automatically dump the code on the GPU, but it's not the case. Once we have installed NetGet, we can check that that everything is properly set up for that. Well, and yeah, all right. So we're gonna go back to talking about quantum states a little bit and how we mathematically describe quantum mechanics, one of the ways, which is through linear algebra. So it should be relatively simple, right? So we say that the state, so all of the information of a physical system, is represented well, at a fixed time by a quantum state, which are these gets that we love to call psi in between bar and this greater sign. But for our purposes, these are just vectors which live on a vector space, and that vector space we just call Hilbert space for when we deal with continuous degrees of freedom. But essentially, these are just column vectors. Okay. Now, what I would like to tell you a little bit is, well, how do we actually construct these vector spaces, right? So before defining what is a vector in this vector space, I need to define how do I construct the vector space, right? And to illustrate this, I'm going to use a very simple example, which is single spin, right? So I will get all of the configurations of my physical system, and to each of these configurations, I will assign an orthogonal axis to each of these configurations. So if the for the spin up configuration, so the arrow pointing up, this is the horizontal axis, the spin down, that's the vertical axis. The quantum state, of course, associated with having the spin pointing up is the vector which is aligned with horizontal axis. Okay, fine. And the one with the quantum state associated with the spin down is the vector which is aligned with the vertical axis, okay? But we can also have superpositions. This is linear combinations of both basis states. This is what we call quantum superposition. This is what the Schrodinger cat analogy is trying to illustrate, and so on, right? And this superposition is defined by the coordinates of this vector along each of the axes, okay? So this is what we actually think of when we are speaking of quantum states, right? These coordinate vectors. Okay. So going back to this, okay, that was for one spin. Now what happens if I want to consider a system which is composed of multiple spins, right? Now the Hilbert space, this vector space of the composite system, is going to be obtained as the tensor product. If you are more in the computer science mathematical side of things, you might call this Kronecker product, okay, of these vectors and matrices. Now the other piece that we need is that every measurable physical quantity, like position, velocity, energy, and Giuseppe has been talking a lot about energy and the Hamiltonian and so on. This is represented by a Hermitian operator. We need it to be Hermitian, so it has real eigenvalues and eigenvectors, right? If it has real eigenvalues and eigenvectors, that means that the physical quantities that I measure are real, right? I don't want to be measuring complex numbers. And these, of course, these operators, they act on the same vector space. And the expectation value of any physical quantity is given by the following quadratic form, right? Where I have the matrix that represents that operator. On the right-hand side, I have the quantum state represented by a column vector. And on the left-hand side, I have the complex conjugate of that quantum state represented as a row vector. There's other postulates from quantum mechanics that that focus on the time evolution of these quantum states, but for what we are going to be doing today, which is finding ground states, so the lowest energy, so the vector that has the lowest energy, we don't need any time evolution, as Giuseppe has talked a little bit about time evolution today. But okay, let's illustrate these postulates of quantum mechanics in this very trivial example where I just have one spin. Okay, the spin can be either up or down. That means a two-dimensional vector space, right? So that's very, very simple. Let me go back to my slides. In this spin system, of course, the vector that represents the spin up is this 1, 0 vector, the spin down is 0, 1 vector, and some relevant matrices, some relevant operators that act on this Hilbert space are the Pauli matrices that form a basis of 2 by 2 Hermitian matrices. So I have sigma x, which is off diagonal, sigma y again off diagonal. If you pay attention, the action of sigma x in this vector is to go from 1, 0 to 0, 1. So sigma x is flipping my spins. And the same happens if I apply to this, to when the spin is down, it will take me from 0, 1 to 1, 0. There's nothing too relevant about that. Same thing with sigma y, flips and adds a complex phase. And well, sigma c is actually diagonal in this basis. So the action of sigma c on the spin up will return the same vector, and the action of sigma c on the spin down will return the same vector with a minus sign. Okay, so let me go back here. And let's consider the Hamiltonian, so the energy operator of a spin which is placed on a magnetic field. These spins you can think of as mini quantum magnets, okay? And their energy depends on whether they are aligned or not aligned with magnetic fields, right? So they will want to be aligned with a magnetic field. The energy operator, for example, if I have a magnetic field aligned with the z-axis, is the value of the magnetic field multiplied by the sigma c Pauli operator. Okay, so in the matrix representation is a diagonal matrix whose eigenvalues are minus b and b. Now the energy of both basis states, remember this is just the sandwich of the matrix between the column vector and the row vector. Well, if I take the ones with the spin up, that's going to give me minus b, and if I take the one with the spin down, that's going to give me plus b. So as you can see, it costs energy to be anti-aligned with the magnetic field, but actually the lowest energy, the stable energy state, if you want, is the one that is aligned with the magnetic field, right? Because that's the one that has the lowest energy in this case. And therefore, the lowest energy state is this spin pointing up. You may be wondering, okay, but why are we talking so much about the eigenstates and eigenvalues of the operator that represents the energy of the system? Well, actually, there's many reasons. For example, is that, well, these eigenvalues and eigenvectors of the operator that represents the energy, they determine the dynamics of the quantum systems. They determine how these vectors evolve in time, right? For example, the part of the dynamics that is the slowest, that's associated with the ground state, with the state that has the lowest energy, whereas the fastest part of the dynamics that's associated with excited states that have higher energy, if you want, in a hand-wavy way. Now, and in particular, why do we focus on the eigenstate or the on the eigenvector that has the lowest energy? Well, it describes also in good measure the physics of low temperature and phenomena that appears at low temperature, like superconductivity, for example. This is captured by the ground state properties of some quantum mechanical systems. And not only that, but also the eigenstates of the lowest energy value can help us understand what are the stable configurations of constituents of matter. For example, what is the shape of atomic nuclei? We know that the shape of atomic nuclei is actually not spherical for very heavy atomic nuclei, but it's more like a pear-shaped, and those are ground state calculations. We can also find what are the stable configurations of molecules. We can study reaction pathways, right? And of course, this has applications in drug discovery and so on. So discovering the ground state properties of a quantum mechanical system is very relevant. And actually, I think on Monday, we are going to try to solve a molecule using these types of techniques, but not today. Okay, that was what happens if I apply a magnetic field on the z-axis. Now what happens if I apply a magnetic field on the x-axis, right? Now the corresponding operator is not diagonal anymore, right? But I mean, I can diagonalize this thing very easily, right? By hand almost, well, by hand directly. And the two eigenvectors and corresponding eigenvalues, the two eigenvectors I'm going to label by arrows pointing on the horizontal direction. So the arrow pointing right, which is 1 over square root of 2, 1, 1. That one is one of the eigenvectors of this operator, and it has energy minus b. Again, this is the spin being aligned with the x-axis. And then the other eigenvector is 1 over root 2, 1 minus 1. This is the spin that is aligned, anti-aligned with the magnetic field that I'm putting on the x-axis. And once again, you can see that one of these eigenvalues is plus b and the other one is minus b. So the lowest energy eigenstate is the one aligned with the magnetic field. Okay. Great. So this means that once I apply a magnetic field to these quantum spins, they want to get aligned with the magnetic field. And again, I mean, I can just use NumPy to diagonalize this very simple Hamiltonian, right? So B equals 3. The Hamiltonian is minus B times the matrix that is 0, 1, 1, 0. So this matrix that I've written here, then I can just call the linear algebra modules of NumPy to perform that diagonalization, and it will return the first eigenvector is, well, here it has a minus sign in, yes.
Are we supposed to be following along?
No, I haven't set it up that way. Yeah, sorry. Yeah. Maybe I should probably do that for Monday. Anyway, yeah. Okay. But okay, that's okay. We can, of course, do that on NumPy, just diagonalizing this matrix. As you will see, the first eigenvector that it returns is the one that has energy minus B. It's not 1 over root 2, 1, 1, but it's minus 1 over root 2, 1, 1. In quantum mechanics, we don't care about overall signs or phases in the wave function. That's because they cancel out once we are doing these types of operations. So overall phases don't matter. So as long as I have the minus sign on both components, that's okay. And then the other vector is minus 1, 1. Great. But now instead of solving this using a diagonalization type of routine that comes with a linear algebra package, we're going to try to solve this problem variationally, okay? So now, instead of specifying what are the two vector components, what I'm going to do is I'm going to define a function. And as you will see, is definitely define a function in the Python sense that is going to take as an input a numerical representation of my quantum state, right? So if the spin is pointing up, that numerical representation can be +1. If the spin is pointing down, that numerical representation can be -1. And that function is going to return, is just going to be a function of that quantum configuration. And then it's going to have a parameter here. Sigma is what I call the quantum configurations of this spin, so +1 or -1. And theta is simply going to be the variational parameter that I'm trying to adjust. So in this very simple case, as this is a two-dimensional space, I can actually write out all of the components if I parameterize things this way. The first component is cosine theta 1 - 1, right? Because that's the one for the spin up. So the first component here is just 1 on this vector. The second component is the cosine theta 1 - -1, so cosine 2 theta. And then I need a normalization factor. The normalization factor is very important, so then the probabilities are conserved. Well, the probability is represented by this quantum state sum up to 1. Great, so this is actually what I'm doing here. I'm going to be using JAX for this. And again, I'm going to be using JAX because I'm going to be able to call automatic differentiation subroutines within JAX, and they are going to take the derivatives that Giuseppe told you today about of the wave function amplitudes with respect to the variational parameter, which in this case is theta. So here I define psi, for which the first input is going to be the label of my quantum state, and the second input is going to be the variational parameter theta, and then it spits out the cosine of theta times 1 minus sigma. Okay, so this is just very simple. Now, the goal is to find the optimal value of theta such that the expectation value of this Hamiltonian is minimized. And we're going to do this using a gradient-based approach, right? So now I'm going to define another function, which is the energy. Again, it's going to take as an input theta and the value of the magnetic field. Before doing anything else, I'm going to find what is the numerical representation of the both of my quantum states. So spin up sigma 1 equals to 1, and spin down sigma 2 equals to -1. Okay. Now, what I'm going to do is I'm going to construct this column vector based on the amplitudes of my variational parameters. So what I'm going to do now is construct this object right here. So I'm just going to make it an array of psi of sigma 1, so psi up, and my variational parameter theta, which is one of the inputs of this energy function, and psi of sigma 2 theta and this. So I'm going to put psi sigma 1, psi sigma 2 in a column vector. Right, with the same variational parameter. And then what I'm going to do is I'm normalizing psi. So this other line, I'm just dividing by the square root of the sum of the squares of this amplitude. So this is what this term here is. And then, well, I have to define what is the matrix of the Hamiltonian. So minus b, again, this matrix that I had right here, which is 0 minus b 0. Great. And then the actual value of the energy, which is the matrix dot the vector dot the vector transposed, right? So essentially, what I'm doing is this operation here. So something relatively simple. Great. Now I have defined. Yes. Oh, because yeah, I mean it's a scalar product, but the shape of this thing is 1, 1. I mean, I could also just squeeze it, and it would just give me a float. This is because I haven't been very careful about it. Don't worry too much about it. Yeah. I mean, it just returns. I mean, it's one number, but it's an array that's of size 1, 1. Yeah, it's to obtain a scalar. Yeah, it's great. Okay, so now let's explore what is the energy on the parameter space, right? So here I'm going to just propose a set of values for my variational parameters that is going to go from 0 to 2 pi, 100 of them. Then I'm going to evaluate the energy for those for that collection of variational parameters. So something extremely trivial. And now I'm going to plot it. Now, as you can see, the minimum value of the energy occurs essentially when theta is equal to 2 pi. So this is this is the energy landscape that my gradient-based optimization of the energy is going to be doing. If we find the minimum value of the energy, which is in this case is -3, we will have found an approximation to this ground state. So I'm going to do this optimization by hand. Okay, so from JAX, I'm going to import their gradient subroutine. And that's extremely easy to use. So if I call gradient and the first entry of the gradient function has to be the function that I'm going to be taking gradients with respect to, which in this case is the energy. And if you remember, when I defined energy, the first input of the energy function was the variational parameter. So what I'm telling JAX here is take the gradient of the function that computes the energy, but take the gradient with respect to the first input to that function, which is the variational parameter. Okay. So this is what this is doing. And then whenever I call energy derivative, it's going to compute the gradients of the energy for me automatically. I set a learning rate for the gradient-based optimization. I'm going to run it for 100 steps, an initial value of theta here theta equals 2, that means that I'm going to be starting somewhere here, okay? So, and then I'm just going to set up some vectors to store the energies for each step of the optimization and store what is the value of theta at each step of the optimization as well, nothing crazy. Store the value of theta, store the value of energy at each iteration step, and then update theta according to gradient descent, right? So theta is going to be theta minus the learning rate times the energy derivative with respect to theta. And here the 3 is the value of the magnetic field that I'll have been working with. Okay, and also here, if you can see that I'm using this TQDM in front of this iterator for the loop, that's just a progress bar. So there's nothing special about it. Okay, so it's finished. And then what I can do is I can plot the energy as a function of the gradient descent step, and also how theta has changed in this gradient descent. So the energy as a function of the gradient descent step, as you can see, it converges essentially to -3 as we wanted it. So we have found the exact representation of the ground state of this very simple model. And then the value of theta, as you can see, is going towards pi, as we have expected. Great. But that was a very, very simple model. Now I can do something a little bit fancier. Now, instead of having one variational parameter, I'm going to have 2 variational parameters. Completely crazy. So the wave function amplitudes now, so remember, this sigma is 1 if you are asking for the vector component associated with having spin up, and -1 if you're asking for the vector component associated with having the spin down. That's going to be cosine theta 1 plus sigma and the exponential of theta 2 1 minus sigma, okay? So again, if I find the vector representation of this quantum state is going to be something along the lines of 1 over the normalization factor, which I'm not writing here explicitly, cosine of 2 times theta 1 plus 1, that's the corresponding amplitude for having the spin pointing up, and 1 plus the exponential of 2 times theta 2, that's the amplitude of having the spin pointing down. So I'm just going to define that. Now, psi is sigma here is going to be simply something that I can iterate over. It can be a list, it can be a NumPy array, it can be a JAX array. So can be sigma again is plus or minus 1, but is theta the one that is can be a list of variational parameters, it can be an array of variational parameters or anything like that. Because the way that I'm coding it up is that psi is simply cosine of the first element of theta 1 plus sigma plus the exponential of the second element of this theta 1 minus sigma. Okay, that's defined. Now we can also explore what is the energy landscape for this wave function ansatz, and that's again the same thing that we did before. Theta 1 is going to be, we're going to sample theta 1 from 0 to 2 pi. Theta 2, we're going to sample it from -10 to 2. And then here, this loop is going to be evaluating the energy at theta 1 and theta 2. But I don't know if you've noticed, but I didn't have to redefine the... I only had to redefine the variational ansatz. I did not have to redefine the function that evaluates the energy. That was written generically enough, so I can just redefine psi, and that works. Okay, this is going to take a little bit longer because I'm looking through it's going through 2 loops with 50 iterations each. So, but great, now it has explored the energy landscape, and this is what the energy landscape looks like as a function of theta1 and theta2. Now you see that this is a little bit more complicated than before. Essentially, the ground state is hidden on these valleys. Okay, so this is the regions with the darker regions are the regions with minimum energy, and in this landscape, you have a lot of degenerate minimums, right? You don't care to which one you converge. You just want to converge to a region with low energy, and then here in between these valleys, there's also mountains and so on. So this is a little bit of a messier loss landscape, and we can visualize it a little bit more carefully. These are the valleys that I was mentioning here. So essentially, I just have to do gradient descent on this loss landscape. Yes.
That's a more general question. So looking at spin models, so response to splits of letters, I guess the usual situation would be that you have rather trivial high energy freedom, but then you have the intensity only low energy freedom around the ground state. So how do you avoid your solver from just oscillate in a kind of sharp canyon?
Yeah. Okay, so that's a very good question. We're gonna do like more complicated systems in a little bit. This was a little bit of a warm up, but yes, the loss landscapes of these variational ansatz are completely messy, are extremely messy, and this is a big problem to the things that we are doing. Some things that you can do, of course, are just starting your optimization in a bunch of different places and see where you converge. The one that converges to the lowest energy is, of course, the best representation of the lowest energy quantum state. Although, yeah, what you're saying is a real problem that we don't have a very concrete answer to, which is how do we deal with very messy optimization landscapes? One trick that we use, which is something that Giuseppe didn't have time to tell you today, but maybe I can tell you a little bit more about it on Monday, is, I don't know if you remember on today's lecture, he defined the Fisher information matrix for these quantum states. Well, we can use that object not only to do time evolution, but also to improve the optimization of these variational ansatz. And this is because this optimization that I'm doing right here, I'm assuming that the parameter space is Euclidean space, okay? The distances are just theta1 squared plus theta2 squared. But that's completely arbitrary. That's an arbitrary choice that I've done, right? What we can do is what computer scientists would call natural gradient, which is find another metric for the space of parameters. And that metric for the space of parameters is defined by that Fisher information matrix that Giuseppe has shown you today, but he didn't have time to discuss the connection with these types of optimizations. That makes the loss landscape much better for us.
Is that somewhat related to using a second order method that was tested before?
Yeah, very much related to that. Yeah, precisely. Okay, so that's the loss landscape. Again, we're even going to recycle the same optimization loop that we used before. Again, gradients of the energy function. Again, here only with respect to its first input. And then I'm just going to iterate and update the variational parameters according to the gradient, standard gradient descent rule. If I wanted to change it to natural gradient, I would have to multiply by the inverse of the Fisher information matrix here, and that would just take care of changing the metric of my space. So, okay, we optimize. We see once again that we have converged now to the -3 energy G that we were looking for. So we have found a good approximation to the ground state with this parameterized model, which was different to the previous one. And we can even see the walk that we've done in parameter space. We have started here and we've landed in one of the positions of this valley here. Okay, but now, okay, systems of many spins, because a single spin was very simple to solve, right? And it's a 2x2 matrix that I can just diagonalize with whatever I want to use, right? Now we want to study a system of n spins that interact with each other. We'll see later how they interact with each other. But the first thing that we need to do is construct the Hilbert space for the n spins. And as I mentioned before, we are going to use the tensor product or the Kronecker product of the different Hilbert spaces. So now the basis of the n-spin Hilbert space is constructed as the tensor product of all possible combinations of the basis states for each individual spin. So this sigma label that I'm going to be using in general actually labels sigma 1, sigma 2, sigma 3. So the state of a spin 1, state of a spin 2, state of a spin n. And that is the tensor product of these vectors that live on two-dimensional vector spaces, okay? And remember that sigma I is plus or minus 1. So then in this particular case, if each side can be in plus or minus 1, that means that the total number of configurations that I have is 2 to the n, right? If I have n sides, something simple. And this comes because the dimensionality of the n-spin Hilbert space is the product of the dimensionalities of each individual Hilbert space, 2 to the n. But how bad is this scaling in practice actually? Well, if we are trying to solve, some spin chains, well, 2 to the 2 is 4. I can solve 2 spins very easily. Even if I want to do 10 spins, well, now the dimensionality of my matrices and vector is 1024. Okay, fine. 20 spins is 1 million. We can, if we do this in a smart way, we can also use exact diagonalization routines to solve this problem. But if we want to solve a chain of 100 spins, now you get to the dimensionality of these vectors is 10 to the 30. So you cannot even store one of these vectors, and of course, even less manipulated to do any linear algebra operators in it. So this is where the notion of a variational state becomes really useful, right? Because instead of having to store and manipulate these 2 to the n vector components, what I have is a function. I give a function a label of my quantum state, and that function is going to return the corresponding component of the wave function, right? And in practice, the way that we do this is if we use neural networks, as Giuseppe has been telling you about, consider this very simple system again that has 2 spin, and consider that we are living on the subspace where you can have either spin down and spin up, or spin up and spin down, right? Now, instead of storing V1 and V2 explicitly, what I can do is, okay, now I want the coordinate of this vector along the horizontal axis. I'll take the corresponding physical configuration, which is down up. I can find a numerical representation of that configuration, which is that, okay, if the spin is pointing down, I'll put a 0 on the first element of the vector. If the spin is pointing up, I'll put a 1. Then I'll run it through a function. In this case, it's a neural net, and that neural net should give me the corresponding vector component. Now, if I want the vector component associated with the other configuration, well, again, find that numerical representation. Right now, the first one is pointing up, so I'll give it a 1. The second one is 0. Sorry, it's pointing down, so I'll give it a 0. Run it through my function, and that should return the corresponding vector component, right? So this is what we are going to be doing. This is what Giuseppe has been telling you about. But okay, before doing that, let's see how we can actually construct operators and things like on vectors on these larger Hilbert spaces using tensor products or Kronecker products. Now, consider the case of 2 spins, right? two spins can either be both pointing up, first one up, second one down, the other configuration down up or down down, right? So this is what I'm representing here. One is up up. The tensor product of both states is represented by the vector 1 0 0 0. Up down is 0 1 0 0. Down up is 0 0 1 0, and down down 0 0 1. And we can actually do this on NumPy. If the state of a single spin pointing up is 1 0, which is here, what I'm showing here, and the state of the same spin pointing down is 0 1, I can use the Kronecker product to construct these spaces. So if I have 1 1 is Kronecker product of up up, 1 minus 1 Kronecker product of up down, minus 1 1 Kronecker product of down up, and the same for the last one. So, and as you can see, if I print the output, it generates the set of vectors that I've told you about before. So 1 0 0 0 0 1 0 0, and so on. That's for states. But now, what happens for operators, right? What happens if I have operators acting in the n spin Hilbert space? How can we construct that? Well, actually, it's the same thing. We just use the Kronecker product, right? So we know sigma c is this Pauli operator that was 1 0 0 minus 1, as I'm showing here. I'll use the Kronecker product to show what this sigma c acting on the first spin and sigma c acting on the second spin looks like. Again, this is a diagonal operator in these spaces, and it has 1 minus 1 minus 1 1. Now, imagine that my energy operator contains terms which are sigma c, right? There's two states here in the middle, the second and third state that have lowest energy, right? Minus 1. Those two states are, if we look at it, is 1 minus 1 minus 1 1. So both the spins want to be anti-aligned. So what this type of operator is represent is anti-ferromagnetic interactions between my spins. They don't want to be anti-aligned. They don't want to be aligned. So we're going to use this notion of these spins wanting to be, well, and this is because I've taken the positive sign in front of this. If I had put a negative sign in front of this sigma c term, now the lowest energy eigenstates would have been 1 and 4, and 1 and 4 correspond to both the spins being aligned, either up or down. They don't care about which configuration they are aligned. So we can use this intuition to build a more interesting model to just having one spin aligned with a magnetic field. What we can do is we can have a chain of 20 spins in this particular case. They're going to interact with their nearest neighbors in such a way that they want to be either aligned or anti-aligned, and control whether they want to be aligned or anti-aligned with a sign of V here. And then they also want to be aligned with a magnetic field along the x-axis. So these spins will want to be aligned with each other, or so they want to get aligned with a magnetic field along the x-axis. This is a transverse field Ising model. And when we are writing these types of operators, sigma c I, sigma c I plus 1 in an n vector Hilbert space, what we really mean is that the identity is acting on the first qubit, on the first spin. The identity is acting on the second spin up until when we get to the ith spin, where we act with sigma c. Then I plus 1 we act with sigma c, and on the rest of the spins we act with the identity. Okay, because again, these operators are only defined on the full n spin Hilbert space. They are not defined on 2 spin Hilbert space. We're going to use periodic boundary conditions. So this is not a chain, it's more like a ring, if you want, of spins. So now, okay, we're starting to use netget now. Netget actually defines these Hilbert spaces for you. You don't have to do this by hand, because if I wanted to do this by hand, for example, I would have to keep track of all configurations, right? Like up, down, up, down, whatever configurations are, and I have to the end of those. So netget does that, all of those things for us. So here I'm importing netget as nk. I say, okay, I want that chain with n spins, and I'm going to use the Hilbert module of netget to construct a spin chain with n spins. This 1/2 label here, well, the physicists will recognize that this 1/2 just means that the spin only has 2 states, either up or down. But netget can actually deal with more complicated local Hilbert spaces where you don't only have 2 configurations, but you may have an arbitrary number of configurations locally. We can check what is the dimensionality of this Hilbert space, right? So we have 20 spins. As we saw before, that's essentially 1 million different configurations. So the dimensionality of this vector space is 1,048,576. Okay, and okay, netget. So it's going to be thinking of these states as strings of +1s and -1s I have introduced in the 1 and 2 spin cases. So if my Hilbert space is sufficiently small, I can actually ask netget to generate all of these possible configurations of the spins, right? So this is I call this method all states on my Hilbert space object that I've defined here. And then I'm going to just print what are the first 10 configurations. The way netget orders these configurations is that the first configuration is the one of all spins pointing down. Then the second configuration is all spins pointing down, but the first one is flipped. Then the third one is all spins pointing down, but here the second one is flipped. So it's using almost binary strings for this. So if you want, this is 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0. So it's using almost a bit string representation of these up and down states. I can also ask this Hilbert space object to return what are the states associated with different indices of my basis, right? Remember, my basis has a million of these different configurations. I can ask for configuration 0, configuration 2, and configuration 3, for example. And again, 0 is all pointing down, 2 is this other one, and 3 is whatever, this other one. But also, not only that, if you give me a configurations of +1s and -1s, I can also ask this Hilbert state object to return what is the index of the basis of that thing, right? So remember here, all quantum states that I generated are all of these possible +1, -1 configurations. If I pass the first 10 back to the Hilbert space and I ask, okay, what is the order of all of these states in the basis? Well, it will tell me, okay, the first one is of course 0, 1, 2, 3, 4. Okay, so it's consistent. You saw that a very fundamental part of the process is sampling states, okay, sampling configurations of the spins. This is what the Markov chains were doing. But before sampling, I need to generate random configurations. So this Hilbert space object also generates random configurations of spins, right? And it does so by this method that we can call random state. Takes as an input a JAX random state, so pseudo random number generator, and then here you tell how many random states, how many random configurations of spins you want to generate. 3 in this case is generated, 1, 2 and 3 different configurations of the spins. Okay, we have a Hilbert space. Now we need to define the Hamiltonian. We need to define this humongous matrix. Netget is actually never going to store this humongous matrix, but is mostly going to retain a symbolic representation of this matrix and how these different terms of the Hamiltonian act on the basis states more than storing the full 2 to the n matrix. So from the operator module of Netget, we can import sigma x and sigma c, the Pauli matrices. And it actually has a very nice syntax that we can operate on these objects sigma x and sigma c as if we were, operating, if you want, yeah, I mean, as if you were writing it on paper, right? Yes. Yeah. So Netget, the way Netget works actually is it only accepts. I mean, you can try to pass a humongous operator to Netget, but it will most likely take forever to compute anything. The most efficient way that you can work with Netget is passing operators that are only acting on a few sites. Whenever it receives those operators, what it knows how to do is how those operators change the basis elements. So, for example, okay, the action of sigma x was, so if I had up, sigma x acting on up, return down, or if I had sigma x acting on down, we return up. Okay. So in my Hamiltonian that I'm defining here, there's the sum of sigma x's, right? But Netget, so sigma x in the one spin Hilbert space is 0, 1, 1, 0. In the 2 to the n space, it would be 2 to the n by 2 to the n matrix. So Netget is never actually computing this object, but the way it does is, okay, I know the matrix is this thing on the local Hilbert space. Now, if you pass me a configuration, let's say that is up, down, and I have sigma x acting on the second spin, what Netget is going to keep is, okay, I know that if I act with sigma x on this configuration, the action is simply to flip that. So it's just going to be aware of these types of changes on the basis states. This is why Hamiltonians and so on are written as sums of k-local terms. So they are terms that act only on a few sites, because you can keep track of these flips explicitly without having to construct matrices at all. That's essentially what's going on under the hood. So the first term that we are going to add in the Hamiltonian is this sigma x. So this term is the sum of gamma times sigma x acting on the Hilbert space hi and is acting on site I. And then, well, and as you can see, writing the Hamiltonian itself is actually, the syntax is extremely simple. And now what we are going to write is these sigma c terms, where v is here going to be -1. If I put v equals to -1, this is going to favor spins to be aligned with each other. And again, just the sum over this list of v times sigma c acting on site I, sigma c acting on site I+1. This part here is to include periodic boundary conditions. So whenever I get to site L, that is going to return 0. So site 0 and site N, sorry, talk to each other. So pretty trivial. Now, even though I've told you, okay, this matrix is 1,000,000 by 1,000,000, yes.
What kind of object is H now? Is it like a netcat?
It's a netcat object, yeah, it's essentially a class within netcat. And it has a bunch of methods and that you can use. And in particular here, what we are going to use is, we are going to ask netcat to actually construct this 2 to the n by 2 to the n matrix, which it can do if the Hilbert space is sufficiently small. And well, this is going to take a few seconds, but again, it's going to construct all of the matrix elements, but it's going to be using SciPy's sparse linear algebra representations of matrices and vectors, so things are a little bit more efficient. So again, it's telling me that it's 1,000,000 by 1,000,000 matrix, and we can use SciPy's sparse module to look for the 2 lowest here eigenstates, essentially, through this function that finds eigenvalues and eigenvectors of Hermitian matrices, because H, remember, is a Hermitian matrix. Again, this is just going to take a few seconds. This function of SciPy linear algebra is actually not doing full diagonalization of that matrix, because probably you would not be able to run the diagonalization procedure there, but it's using a Lanczos type of algorithm, which quantum physics people use all the time. But anyway, these are the eigenvalues of the exact diagonalization of this matrix, the 2 lowest ones. So we know that the energy of the ground state is minus 25.49 essentially, and the first excited state, so the eigenstate that has the energy just above the ground state, is minus 25.41. Okay, now we're going to be working with this very large Hilbert space, and we're going to be defining a quantum, an ansatz for this quantum state. So remember, I pass one of these configurations to a neural network, and it's going to return the associated wave function to that configuration of the spins. So this is what I'm writing here. I know that the ground state of this model, actually the wave function components don't have any signs. So all of these vector coordinates are positive. So the model that I'm going to use is the exponential of the output of a fully connected feed-forward neural net. The way that netcat is asking for these types of models is not for you to pass a function that returns wave function amplitudes, but to pass a function that returns the logarithm of wave function amplitudes. And this is because essentially when we were, when Giuseppe told you that in order to compute the gradients of expectation values that you were estimating, you needed this O operator that he was writing, which are 1 over psi of sigma, the partial of psi of sigma with respect to the variational parameter with respect to theta of sigma. You need these types of objects, but at the end of the day, this object is just partial with respect to theta of the logarithm of psi of sigma, which is why netcat asks for the logarithm, or for you to define the logarithm of the wave function instead of the wave function. It also asks for the logarithm of the wave function instead of the wave function itself, because when part of the algorithm is computing ratios of the wave function evaluated at one spin configuration, other spin configurations, sigma, sigma, sigma prime. But you see that this can give you numerical instability, right? This is very small and this is very large. This might give you numerical instability. But if you compute it in log space, you're just subtracting two numbers. Much better. So this is why when you give a model to Netget, you have to give the logarithm of the wave function amplitudes. As in this case, I've chosen to represent the wave function amplitudes as the exponential of the output of a neural net. I'm just going to pass that neural net to Netget as the variational ansatz. And here the model can be defined using one of the several functional JAX frameworks, like JAX-Stacks, Flax, or Haiku. Essentially, what you need is something that initializes the variational parameters and something that can evaluate your model, a function that evaluates your model. In this case, we're going to use Flax because it's just much easier to write these models. So you define a class, which is a neural net module. Linent here of Flax is the repository with different layers, initializers, and nonlinear functions to construct neural nets very quickly. And essentially, you just need something that is going to call this dense layer from Flax and apply it to an input X, and then apply a ReLU activation function, because why not? And then just sum the output of that, and that's going to be the amplitude of my, well, the logarithm of the amplitude of my wave function. As you can see here, the input X are going to be these vectors, so +1, -1, -1, +1 of the configurations of the spins. In particular, this model dense here alpha times the shape of X -1. This is so if I pass an input that has length 10, then the output of that layer is going to produce a vector that has length alpha times 10. Then I'm going to run a non-linearity on all of the coordinates of that vector of length alpha times n. Alpha is a hyperparameter of the model, by the way. I can just choose how wide I want my hidden layer to be. So then I apply that, and then I apply a non-linearity to all of those outputs, and then I sum them all together. So that's simple. Yeah, this is all real coefficients. Yeah, I'm just gonna, yeah, this wave function doesn't have signs, essentially. So this, although we can also do complex coefficients with Netget, but in this particular example, I'm just gonna make them be real. So again, this model is just a set of instructions to initialize parameters. The parameters here are being kept track of by this neural net dense module from Flax, and then something that evaluates the model itself. So this is the model. Here we're going to initialize it with alpha equals 2. So if I pass an input vector which has dimension 20, it's going to return an output vector that has dimension 40. Okay, and then sums everything together. Then something that was essential on variational Monte Carlo is something that can sample these spin configurations. And we're going to include that through a Netget's module sampler. This is going to be Metropolis Hastings, as you've seen today in the class. And that requires you to specify, of course, what is the Hiller space, so it knows what are the possible configurations of your spins. The number of chains of the sampler, so that is, instead of just choosing one initial configuration and running one of these Markov chains and generate different configurations, here in this case, I'm going to start 8 different chains, and I'm going to let them time evolve. yeah, and this number of sweeps equals 1 is so because sweeps you can actually skip samples if you want to. But yes, again, this Metropolis local sampler, what it's doing is you give me one initial random configuration of the spins. I choose a random one of the sides of the lattice. I flip the spin, and then I accept or reject that move according to the ratio of the wave function amplitudes, as you've seen today with Giuseppe. So yeah, essentially, yeah, that defines the sampler. And once I define the sampler, I'm going to define what is my variational quantum state. And again, this is done through Netget's module VQS and Markov this MC state, okay, which requires for you to specify what is the sampler, what is the model, so what is the logarithm of the wave function amplitudes that you want to use, and the number of samples that you're going to be collecting, in this case, 20 by 4,000. And then you can initialize the parameters of the model with like any random initialization. Okay, so what does this V state contain actually? Okay, so it's aware of the Hilbert space that you're using. It knows what the sampler is and what the transition rules are in the Markov chain. It knows how many chains you're using. It knows that it has to sample this machine power equals to, it knows that it's sampling from psi sigma squared. This is the machine power. You can sample from other powers if you wanted to, but we can just leave it at 2. And of course, the number of samples that we have specified. We can also ask what are the parameters of the model that we have, right? So this variable, so we can access the different parameters, which in this case are stored as nested dictionaries. So here we only have one dense fully connected layer, which is, this is what it's telling me. I can access what is in that dense fully connected layer. And of course it has what it calls kernel, is the matrix multiplication that it's doing. And it has a bias, which is adding a vector to that output, right? And of course, okay, the bias has length 40 because the vector that I'm producing is 2 times 20, 40. And the matrix multiplication that is doing, it has shape 20 by 40, right? Because as an input, I take a vector of length 20 and I produce one that has length 40. And well, as part of the sampling, I can actually just generate samples, ask Netget to generate samples from this mod psi squared. So I've asked it to generate 80 samples. And what it's doing is, okay, I told it to use 8 chains, right? To generate these samples. So if I ask for 80 samples, what it's going to do is going to distribute those 80 samples across the 8 chains. So each of the chains are actually going to be just collecting 10 samples, 8 chains, and then this other length is the length of the space of spins that I'm using, which is 20, right? So again, what Netget would return is just matrices. Well, it's a tensor of +1, -1, -1, +1 according to these spin configurations. Okay, now we go into, yes.
So this came from your MCMC sampler?
Yeah, this came from the MCMC sampler. Yeah.
So fast?
Yeah. Yeah. The very nice thing about Netget and JAX is that Netget is using JAX just-in-time compilation tool. So the first time that you run things is compiling everything. But once it has compiled everything, then it runs very, very fast. Great. Now, expectation values. I need to compute these types of objects, right? Which is sandwiching my matrix between a huge vector column and a huge row vector, right? And of course, this sum is going to have 2 to the n squared terms, so it's completely untractable. I cannot even if I'm not even if I'm. Do you guys have any questions? Okay. Even if you have like vectors of length 2 to the n, but you are not explicitly defining them, you're just asking for their components. Even if I have to perform these sums, this is completely untractable, right? So what we are going to do actually is, as Giuseppe mentioned, what has been describing to you is, okay, when I write this expression, I'm going to insert one resolution of the identity here. The resolution of the identity is simply this linear combination of brass and kets. This is just writing the identity matrix as the product of column vectors with row vectors in this very particular way. So you're just not doing anything. But you can rearrange the terms of this sum to look like the sum over all possible spin configurations, the modulus square of the wave function, which is a probability distribution, as you know, and then this other thing. This other thing is what we call the local operator, and it contains the sandwich of the basis elements with the operator itself and the wave function, the parameters wave function that you have, divided by the wave function evaluated at spin configuration sigma. And what we are going to do is we are going to approximate this sum as the regular average of this quantity evaluated at spin configurations which are sampled accordingly to this probability distribution defined by psi squared of theta, which is what Giuseppe has told you about today on the class. But wait, so I wanted to first estimate this expectation value. And then I've told you, okay, I can just estimate it as the average of this other quantity here. But wait, this quantity here is also an expectation value. Like, have I just, you know, have I gained anything by rewriting things this way? Well, the thing is that these operators are extremely sparse in the basis that we are choosing, right? And this is what I was telling you before, is that if I have, let's say, sigma x acting on one of these many spin configurations, the only thing that it's doing is flipping one spin. So the action of O on a basis element is just flipping one spin. So that's actually very simple. And what this expression usually boils down to is, again, computing ratios of wave function amplitudes evaluated at 2 or a few different configurations of spins. And well, we can actually do this with netget as well. Now we're going to tell our variational state to, instead of using 80,000 samples, to just use 4,000 samples to have things run a little bit faster. And we're going to ask to estimate the expectation value of the Hamiltonian that we wrote before. And this generates actually an object of types stats, which is a type which netget defines, but you can actually access whatever is in the statistics of the expectation value in terms of a dictionary. So it contains the mean of the expectation value of the Hamiltonian, the energy, it contains the variance, it contains the error associated with that expectation value. So sigma divided by the square root of the number of samples. Then it contains this thing that is calling R hat, which is the Hellman-Rubin diagnostic, that essentially is a diagnostic to know whether your Markov chains have converged and whether you have explored the space of configurations in your probability distribution correctly. And then it also returns the autocorrelation time. Typically, as a rule of thumb, you want this R hat to be, so R hat equals 1, that means perfect sampling. You don't want it to be bigger than 1.1 roughly to know the sampling, that the sampling is working well. Okay, so now we can sample from the wave function, we can compute this expectation values. Okay, now we can optimize our wave function finally. So what we are going to do is we're going to do an optimization by hand, just a gradient-based optimization by hand. Here, energy history again is to store what is the value of the energy. In the optimization, we're going to use 1,000 steps. We ask this variational state from netcat to generate the expectation value of the Hamiltonian and also the gradients of the expectation value of the Hamiltonian, which is what Giuseppe has told you about today, how that's done. We just store what is the energy at each step on this energy history list that we've created. And now what we're going to do is we have to update the parameters, but the parameters are stored in nested lists. Another thing that JAX does extremely well are Python trees, okay? And it knows how to handle Python trees, and in particular nested dictionaries are a Python tree. So what we are going to do here is actually update the parameters using this JAX tree multimap functionality, which is, it does exactly the same operation in all of the leaves of a tree. So essentially what we are doing is updating the parameters according to the gradient with the energy. So we are going to let this run. For each optimization step here, we are computing, we are using 4,000 samples to estimate the expectation value of the Hamiltonian. And remember, we are dealing with a Hilbert space which has dimensionality 1 million, right? And still this is running on my laptop relatively fast. So I would say it's working pretty well. While this run, do you have any questions so far? So
No, I mean, the form of the method.
Oh, you can do many things. You can deal with continuous degrees of freedom as well, if you want to. You can do and essentially define any type of local Hilbert space that you want. It doesn't have to be spin. You can define something that has arbitrary dimensions and then define operator. Spins, no, sorry, fermions are a little bit harder to do. I will be discussing fermions on Monday. But yes, the short question is yes, there's a module right now to do fermions, but it's not as simple. But yes, we can do the Hubbard model. And we can do the Hubbard model on Monday, maybe. Okay, so this has finished. This is the energy as a function of the optimization step. Great. This blue line is the actual ground state energy that we have computed at the beginning using this exact diagonalization trick. And here, okay, so this is the value of the energy that we have computed using variational Monte Carlo, which is minus 25.42. I don't know if you remember, but the exact one is minus 25.49. So the relative error defined as the difference between the exact and the VMC energies divided by the exact energy, that's here of the order of 10 to the minus 3. So we would, in doing research, we would have considered this to be a successful run for the most part. Well, in this case, the system is pretty small, so maybe not. But anyway, we can try to see if we can fine-tune these results a little bit more. To fine-tune these results a little bit more, what we can do is, as you asked before, well, we can try decreasing the learning rate a little bit now, and also compute more samples. So I can change the number of samples that I'm using here very easily. And then I can also use a much smaller learning rate when I update my parameters and run this, let's say for 300 extra iterations to see if I obtain a better estimate to the ground state energy. Because also, as you can see here, this still is going down a little bit. It's not fully converged. So yes. Yes, so, well, one of the problems is that if you, yeah, you're right. If you use Jordan Wigner, now the Hamiltonian becomes a humongous mess and you don't respect any notion of locality. Good question. You can work on first quantization. First quantization, this on Monday, we're going to probably do first quantization where the wave function amplitudes that you are defining now have to be antisymmetric with respect to permutations of the inputs. So if before I was giving you +1, -1, and I permuted these two, the sign of the wave function has to change. But we will see how we can actually do that on Monday. Okay, this has finished. Let's see. Oh, yeah, it seems like fine. We might have improved our energies by a tiny little bit, but okay, I think this is essentially converged. Yeah, actually, the final result of the final error that we have obtained is it actually hasn't improved anymore doing this type of fine tuning. Okay, well, I think that to conclude it's even worse. Yeah, it's a little bit worse, but we are estimating things stochastically, right? So even though I've printed out here an error, I have not printed out the error of the relative error, right? So probably the error of the relative error is bigger than the change that you've seen. Yes. There's no concept of overfitting here because the concept of overfitting when you're doing supervised learning is that you end up just remembering what you learned from your examples. Here, there's no learned examples or anything like that. Yes, that's okay. That's a very good question. But the thing is that on each of the optimization steps, you sample again. It's not like you sample at the very it's not like you sample at the very beginning of the optimization. You obtain a set of samples and then you use those samples to estimate expectation values and everything. Because you're right, if you did that, you could end up very brutally over, if you want to call it that way, over parameterizing it. And also the thing is that would be a huge mistake because the probability distribution at the beginning is a huge mess, but then once it has converged into the ground state, it's probably something much better. It's a completely different probability distribution. So it doesn't make sense to sample at the beginning and then use the same samples as optimizing the wave function because the probability distribution itself is changing with the wave function itself. So after each parameter update, I have to resample, complete the estimate. So energies and gradients and update parameters and resample and so on. That's how we do it. Okay, great. But okay, I had to write my own optimization loop. Netcat also has its own optimization drivers, which make my life much simpler. Here again, I'm just saying, okay, I just want to collect 4,000 samples. I want to reinitialize the parameters because if I don't reinitialize the parameters, it's just gonna take the parameter, the optimized parameters from here, and it's gonna see good energies already. And I'm just going to use the optimizer module, and in particular, stochastic gradient descent. Netget calls this stochastic gradient descent. And you just specify what is the learning rate that you want, which is 0.01 in this particular case. Then you have to use the variational Monte Carlo driver and tell it, okay, I want to optimize the Hamiltonian using a stochastic gradient descent, which is stochastic gradient descent is what Giuseppe has described today. And the variational state that I'm going to use is the V state that I've defined before. And I can just run it. The other thing that is very important, that I'm going to talk about while I run this, is that, well, Netget actually logs the optimization dynamics into its own logging modules. In this time, this runtime logger is going to save the energies at each step and everything in memory, but you can also dump everything into a JSON file while you're optimizing things. So you can just use TensorBoard to visualize things, or you can just open it as a dictionary whenever you want. And then lastly here, this is just running the optimization driver that you have here for 1,100 iteration, and is saying, okay, the output just collected in this logger that you have defined here. So again, yeah, this is again running, collecting samples, estimating expectation value of the energy, derivatives, and updating parameters. Yes. Okay. And actually, one very nice thing here that you can see is that the Netget optimization driver is actually generating the progress bar for yourself, and in the progress bar, it tells you what is the energy in that given optimization step. So here you see that we are already pretty much converged, right? The result that we were looking for is minus 25.49. So yeah, here the final result is minus 25.46, and the error 10 to the minus 3 again, which is pretty good. We can access the logged data through, asking the logger what is the data itself, and again, it's just stored as a dictionary that contains the energy history, the iterations, the mean, the variance, the sigma r hat, and the autocorrelation time of all of the times that it has measured the energy. And yeah, we can just plot the energy convergence and see what essentially we converge to the ground state. And once we have converged to the ground state, we can measure other relevant physical quantities of interest. In this case, we want very accurate estimates of these physical quantities, so we are going to increase the number of samples to 40,000. The type of physical quantities that we're going to be measuring is sigma x acting on site I, sigma x acting on site I plus d, where d is the distance between these two sites. This type of expectation value tells you, okay, if the spin I is somehow tells you what is the correlation between the spin I pointing in the x direction and spin at distance d also pointing in the x direction, right? So if the spin I is pointing in the x direction, this spin of I plus d also pointing in the x direction, or in the x direction, the reverse. That's the type of information that these quantities are going to give you. So while I run this, I'm just going to store all of the results in a dictionary here that I'm calling sigma xx. I'm going to be looping through all of the sites I, and here I'm looping through J. J is going to be computing that those quantities and storing that at in a dictionary, and then I'm just going to take yes. Very good question. Netget right now does not allow you to VMAP operators. It might in the future, but right now it does not allow you to VMAP operators. But yeah, I think someone requested that feature at some point. But I don't know if they're going to do it. VMAP is vector map, so it's vectorizing your operation. It understands that you are repeating the same operation over the dimension of one of the input vectors, and it vectorizes that so you can parallelize things much better if you want. You probably know a lot more about that, right?
But you said if you wanted to write a loop, instead of writing a loop, add the extra dimension.
Yeah. 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 Imagine that you want to multiply one vector by a bunch of matrices. You can store all of those matrices as like a 3-dimensional tensor, right? And then it understands that one of the first dimension is the one that it has to repeat over, right? If you want. Yeah.
But Jax is like, no.
Yes. Okay. So we are on time now, and well, this is the correlations that we are measuring. Essentially, is sigma I times sigma I plus d. This means that, of course, if at 0 distance, if my state is pointing in the x direction, well, itself is also pointing. So this 0 distance doesn't mean anything at all. But what this means is that there is some sort of correlations in my quantum system. There's some sort of entanglement, if you want to think about it that way. If the spin at site I is pointing in the x-axis, there is also some probability that spins far away from it are going to be pointing along the x-axis as well. And this decays as a function of distances, as you can see. And this is some of the things that we are interested in and we measure, and these things characterize what are the phases of matter and so on. So yeah, with this, I think I'm just gonna finish today's tutorial. Yeah, thank you for your attention.